So good morning, all. I just want to do a really quick introduction and welcome and thank everyone for coming out today. We're really excited for what is a pretty packed agenda. So we've managed to cram at least a day of content into a half a day here. So we've got a number of really exciting speakers. I think more than anything, I'm excited to get this kicked off because, as many of you know, we've been working on in the standards space and not necessarily on developing standards in any way, but instead helping to convene the community around what's needed and then coordinate the response by the standards development organizations. So we've initiated all of that work back in 2016, produced an initial roadmap. Tremendous amount of work has gone into it by many of the folks that are going to be talking today. And then there was an update in 18, and I would say that we're now really kicking off what will be an increased emphasis on the standard space from our point of view in coming months at the Institute. So we're excited to get this going because we're using a portion of this activity to talk through some of where the SDOs have gone while being able to bring some important updates from technical projects that have been produced or have been worked on at the Institute that directly align to this, and then have also brought some other technical experts to the table as well. So without further ado, I will hand it over to Brandon, who will be the one actually working through the agenda today and working with Jim McCain from ANSI. So over to you, sir.
Thank you, sir. Good morning, everyone. Thank you so much for being here. It's really is a delight. Just to kind of expand upon some of what John said, I just wanted to kind of unveil some of the logic and thought that went into today's agenda. We've long since been working in this space to expand upon addressing the needs of the technology so that we can help accelerate the maturation and development of standards, right? We recognize that at the core of standards is a wealth of knowledge, and this knowledge can be utilized in a variety of ways. And so, what we'll be having here in just a few short moments is a discussion around not only the technology, but then how that intersects with the standards landscape. And, we've talked to some of you in terms of helping us to develop the content here today. And we hope that you really enjoy it. And so, the discussion is going to be around control and qualification and trying to understand how those are intertwined. And then furthermore, for those of you who go to a variety of these events, we're seeing this trend that there are a lot of things that have been conducted, not only at the Institute, but each and every one of us, when we get out of bed in the morning, we work on. And there's a variety of ways how we can take these lessons learned and transfer them to new technology domains. And I think we're seeing, particularly this year and in the next several years, there's going to be a lot of opportunity there. And so I'm excited that we can start this conversation here today and we can see how we can grow our understanding together. And so with that, I'm gonna welcome Mr. Jim McCabe to the stage. He's going to lead us off with a discussion around the AMSC roadmap. And talk a little bit about that, not only to bring some of you who've been a part of this journey with us, bring you up to speed with where we are and let you know what's coming up in the next year or so, but also to inform some of you who may be a little less familiar with it, and so you understand what we're talking about. Good morning, Jim. How are you doing today, sir?
I'm doing well, Brendan. How are you?
I'm great. It's good to see you.
Likewise, and hello, everyone.
So with that, I will give you the stage, and thank you so much for being here, and thank you all.
All right, terrific. I'm going to try and share my screen here. Let's just make sure. Okay. Let's go to presentation mode. Are you seeing that?
Jim, I think you need to click on the actual application and then you'll be able to share your screen.
There we go.
Perfect.
It's working now. Okay. Yeah, well, thanks everybody. Thanks, Brandon. Great to be here, and really appreciate the opportunity. As John mentioned, we've been working together in partnership, ANSI, where I work, and America Makes for the last couple of years on the Additive Manufacturing Standardization Collaborative. This is going to be old hat for some of you who've been around for a while, but for the uninitiated, we thought to sort of launch the panel discussion that we're going to have in a bit, just to take you through kind of a quick overview of the work that we've been doing to help you better acquaint yourselves. So hopefully they're on slide 2 here now. So going back, as John said, late 2015, early 2016, you know, there was discussion or recognition, I guess, that a number of standards developing organizations, or SDOs as we call them, were either getting involved or had their toe in the water to write standards related to different aspects of additive manufacturing. And there was also the recognition that it would be a good idea to try and promote coordination so that we would end up with a consistent, harmonized, and hopefully non-contradictory set of AM standards and specifications. And really, I guess, you know, the industry historically had been driven up to that point by many company proprietary standards. So this was kind of an idea to move towards more what we would call as voluntary consensus standards or industry standards that would reduce non-value added costs and facilitate the growth of the industry. So this is just kind of a quick snapshot of some of the SDOs who are involved in AM, many of whom you're going to hear from today. Of course, in terms of international standardizing bodies, you have ASTM and its committee F42, which works in close partnership with ISO's committee TC261. Actually, together, they have kind of a unique arrangement within the international standards arena in that they will jointly develop and dual logo their standards. You also have the American Society of Mechanical Engineers, ASME, very active in the design space, getting more active in the medical space. You have SAE International, yet again, another international standardizing body along with ASTM and ASME that is US-based. SAE, of course, heavily involved in the aerospace and automotive sectors. And then there are many others. The American Welding Society has produced its D20 standard. You have IEEE, which is involved, has some work in the medical space. Others in the medical space include the Medical Imaging and Technology Alliance, which is part of the National Electrical Manufacturers Association. AMI, the Association for the Advancement of Medical Instrumentation. You have groups like IPC, which is involved in printed electronics. You have the Metal Powder Industries Federation, UL, which is heavily involved in safety standards, and MT Connect, which is about presentation of data. So again, a lot of organizations involved in this space. Seemed like a good idea to get everybody together to kind of see what we could do working in coordination. So I guess it was around February of 2016, there was a meeting convened at the National Institute of Standards and Technology, NIST, in Gaithersburg, Maryland. And shortly thereafter, we entered into a partnership, ANSI and America Makes. And of course, America Makes, as you all know, is really the nation's leader in terms of, you know, collaborative research on AM. ANSI has been around since 1918. We basically serve as the administrator and coordinator of the U.S. private sector-led, public sector-supported system of voluntary standardization. We're a standards organization, but we don't develop standards. So that positions us kind of uniquely to serve as a neutral facilitator in bringing parties together. So, you know, it really bears emphasis that I mentioned NIST, certainly the Department of Defense, the FAA, and many of the SDOs already mentioned were kind of instrumental in bringing this partnership to fruition that has become the Additive Manufacturing Standardization Collaborative. So we set out, our purpose was really about coordinating and accelerating the development of industry-wide AM standards and specs consistent, of course, with stakeholder needs. And again, the whole idea is to grow the additive manufacturing industry. If you know anything about ANSI, our mission is actually promoting the global competitiveness of U.S. business and the U.S. quality of life through standards and conformance with standards and maintaining the integrity of the system. So it really was kind of the charter here is consistent with our mission. Again, AMSC is not writing standards. Really, it's about trying to drive coordinated activity among the SDO community. So some high-level objectives, first and foremost, we wanted to try and clarify the current and the desired future standards landscape. Again, drive coordinated activity among the SDOs, liaisons, avoid duplication of effort. We wanted to basically provide a stable of subject matter experts who could work with the SDOs and help accelerate the development of AM standards and specs. And part of this is also about informing companies and others where to invest their resources in terms of standards participation. Some SDOs work more horizontally, others are specific to a particular industry sector. Again, all about establishing a common framework of AM standards and specs. The process is open to anybody. All we said was that you need to have operations in the US. So a lot of the participants actually in the AM space I know are non-US based headquartered companies, but they participated in AMSC. You didn't have to be a member of ANSI or America Makes to participate. So we had OEMs, we had precursor material producers, obviously representation from the user community of industry and government, as well as R&D, bringing in academia, the SDOs that I've mentioned. I think for version 2, we had around 300 individuals from close to 200 public and private sector organizations. So it was a really good mix. We did draw pretty heavily from the aerospace, defense, and medical sectors. Also had involvement from the printed electronics and others. But the roadmap basically reflects the perspectives of those who are involved. So bear that in mind as you look through the document. So our deliverable is this roadmap. As John mentioned, we published the first version in 2017, a second version, I guess it's almost 2.5 years ago now. The document identifies published and in development standards. It does a gap analysis and then recommends priority areas where there's a perceived need for additional standardization. We ended up identifying 93 gaps, and we define that as being the absence of a published standard, right? So there might be a standard that's already out to ballot and publication is imminent, but we still said that's a gap just as that demarcation point. When we identified a gap, we made a recommendation as to how to facilitate or fulfill that. So you can get all of this at the URL there, ansi.org/AMSC is the landing page for the initiative. What we've tried to do since June of 2018, we launched just over a year ago, basically an online gaps tracker portal, which we'll be updating over time. And that really seeks, with the input from the SDOs, to provide the latest in terms of what's been happening in the standards arena, to keep this as a living document, not just a point-in-time static roadmap. So again, we'll be hearing more about that from our speakers in our panel today in terms of work that's taken place. And we look forward to ongoing contributions from the community as we try to keep that as valuable a document as possible. So just in terms of how we organized ourselves, and really it's how the roadmap is organized, I guess first I should mention that the front end of the roadmap includes kind of overviews in their own words by the SDOs in terms of their standards work programs. But then the sections that follow that for the gap analysis really are organized around the life cycle of producing an AM part. So you start with design, then you get into the process and materials area, of course, precursor feedstock materials, the whole area of process control we'll be talking about today, post-processing, finished material properties. We had a working group set up for qualification and certification, which is touched on in other sections, but just to make sure we didn't have our own gaps in terms of our analysis, non-destructive testing and evaluation, and maintenance and repair. So those were kind of the 8 primary working groups. But then we also, in the course of trying to accommodate the needs of particular sectors, we had a horizontal working group from the medical community who felt it was just easier for them to kind of look at the document across all of the sections. So they provided content that way and did a yeoman's job at that. And we also, version 1 tended to be kind of metal-centric. So in doing version 2, we decided to establish a dedicated working group on polymers. And we greatly expanded the content related to polymers in version 2. So within each of the subtopical areas, so you have those 8 or 10 working groups that I mentioned, but you will see as you go through the chapters like design that there will be various subtopics. So within each of those areas, there's first a description of a particular issue, like why it's important. Then we move on to a discussion of published standards. In some cases, it may be that the standards that are already out there adequately address the issue, and so there was no gap identified. More likely, the scenario was there is some work underway, and again, the needs are driven by the user community. So the assumption is if the market has identified a need for a standard, then that's a gap. So so then we state what the gap is and provide a recommendation how to address that. One of the things we found as we were going through the process after actually we had published a first draft of version 1 was there, in many cases, is a pre-standardization research and development component associated with this. So we asked the question, is R&D needed, and tried to, in many cases, provide a little more detail on what that is. We also tried to identify the priority, whether it was high, medium, or low. We said high would be, ideally, we'd have a published standard in the next 2 years, medium, 2 to 5, and low, 5 or more. And we have a matrix that I'll talk a little bit more about that on the next couple slides. And finally, we also, to make this kind of a roadmap, we wanted to list 1 or more organizations that could address the gap, both from the standardization perspective, but also from the R&D perspective. Again, the SDOs determine their own work programs based on the needs as expressed by the membership of those organizations. ANSI itself doesn't dictate the work. We don't assign the work. It is all driven by the SDOs. So, you know, this was a real cooperative effort, and I think it's borne fruit, and we've seen that in the work that's gone forward. So just in terms of the priority levels, I mean, we established what we call the CASE approach, which, you know, using the acronym, the whole idea here, I should say, was really to avoid priorities being established just kind of on a subjective level, to give it a more objective basis. So the first thing we looked at was criticality from sort of a safety and quality perspective. You know, how important is the project? If we don't do it, what are going to be the consequences of that? We also looked at achievability, which is the time it takes to complete. Is this something that's brand new or close to completion? How long are we going to take? So we assigned scoring values to those. And similarly, we looked at scope, which is really about the investment of resources. Again, is this something that, to address the gap, is going to require a lot of pre-standardization R&D, or can it be done fairly quickly with what we already know? And then finally, the effect, which is maybe sort of mirrors criticality a little bit, but more on the business side. So what's going to be the impact on the industry of completing the project? So we basically just added up the scoring values, and that's how we came up with the matrix of high, medium, and low. This is a very simple example of what the roadmap provides in terms of a gap statement. And again, in the section, you would see before this the description of the issue, the list of published and in development standards. But we also have at the front of the document a table that just lists the gaps. So this was the first one in the area of process control, and it talked about the fact that, you know, existing process control standards don't adequately address digital format and digital system control. Yes, R&D is needed. Not a lot given there in terms of description, but we do have the identification of leveraging NIST research and work with the SDOs to ensure that the AMS process or AM process control standards address digital format and system control. This one was a medium. So what we did when we got to version 2 was we wanted to compare it to version 1. So as of June of 2018, when we published version 2, this one was underway. There was work in progress. We used a traffic light analogy. You know, green means go. You might have seen orange or red, which for some reason or another, the project was stalled. In other cases, you might see that it was not started, or maybe the gap was closed or withdrawn, or even unknown in some cases if we weren't sure if any SDO or other organization had already endeavored to address the gap. We also had like a narrative statement of the update on the process of work. So as of June 2018, regarding this gap, ISO TC 261 and ASTM F42 had a joint working group 56 that was developing a standard that addressed digital data configuration control. Now, to the point I made earlier, what we've done since then, again, with the input from the SDOs and others, is to try and, you know, keep this up to date. So in March of this year, we had an intervention that the AWS D20 standard includes language requiring a contractor to have a digital control plan in place and defines the items that must be included. Again, the list of organizations, you know, NIST is mentioned here vis-a-vis R&D, ASTM ISO, SAE also, and the IEEE ISO printer working group. And I guess we probably should have had AWS in there as well. But this anyway will give you a flavor of how the information is presented. We try to present it in a consistent way, again, to make it as meaningful as possible. This slide just illustrates kind of where the gaps broke down in terms of high, medium, and low, and across the topical areas. Certainly a lot of work in the design space, in process control and qualification. 93 gaps in total, as I mentioned, 18 being high priority, and 65 of those 93 requiring R&D. So a lot of work underway, a lot more that needs to be done. So what I thought I'd do with the remainder of just this brief overview is just kind of talk a little bit, since we're talking about process control to enable qualification, of some of the topical areas where, well, not just topical areas, where gaps were identified in the process control section. There's a lot of, there's a lot of overlap between some of the different sections of the roadmap, but things hopefully are illustrative of the types of issues that were addressed. So I already mentioned number one there. We got into discussions of the lack of standards for machine calibration and preventative maintenance, machine health monitoring and qualification, parameter controls in the production process is certainly a big area. Then we also looked at things like adverse machine environmental conditions, depending upon where the printer was located, maybe in a shipboard environment. How did that affect component quality? Starting to bleed a little bit into the precursor material section, but vis-a-vis printing, recycling and reusing materials, as well as stratification. Again, environmental conditions, this time looking at the effect on materials. Similarly, again, reusing material that either has or hasn't been processed. Specific gaps related to things like precursor material flow monitoring and flow parameters for material jetting as a process, occupational safety and health. Again, this time looking at it from the standpoint of protecting machine operators. Cybersecurity, which of course is a horizontal issue across areas, in-process monitoring. Then sort of moving over into the post-processing area, we looked at post-processing qualification and production builds. So there's a lot of text, obviously, behind all of these that provides greater detail. This is just kind of to give you a snapshot of some of the things that were addressed. Moving on to the Q&C chapter, and this chapter, the beginning of it kind of identifies a number of resources that exist within the industry related to Q&C. When we started down the gap analysis, the first one here is terminology. Different industry sectors use that differently. The rest of the chapter was kind of broken up into aerospace, defense, and medical. I think there's also a section there on printed electronics. So the next couple, QC2 and 3, I think were introduced by the aerospace sector. AM part classification system, really critical. Harmonizing terminology related to Q&C, specifically related to process parameters. 4 and 5 there were specific needs identified by the defense industry. So there is a gap related to process approval for DoD procured parts specifically, and then DoD's specific needs related to machine operator training and qualification. The balance of the ones on this slide and the next one that I'll show really were from the medical community, although they may have broader application across other sectors. And you can tell by the names here, we're talking about importing ultrasound data, image accuracy phantoms, and so on. Obviously, resorbable materials is huge when you're talking about medical devices being implanted in humans. Segmentation, sterilization, and so on. So again, just a real quick snapshot of what I hope we're going to get a flavor of as we move forward. So I think in the interest of time, I'm just going to sort of move into the panel discussion, and just got a couple more slides to kind of set that up, and then we can introduce our panel members. One of the things that we asked our speakers to think about, and they will touch on this, I think, in varying degrees, but again, since we published version 2 of the roadmap in June of 2018, what have we seen in terms of new standards that have been published, new committees or working groups that have been started, or projects, and to what extent, this is really the $64,000 question, do these developments address the gaps that we're identifying in the roadmap? That's not easy. That is sometimes kind of hard to map, but we're working that problem. Then also we wanted to really just broaden it and have a discussion of current and future trends. So, you know, are the priorities that the group identified 2 years ago are the same, or have they changed? And I suspect it's definitely the latter, given the fast move of this industry. What are you hearing from industry members in this regard, and what new areas are emerging where standards are needed? So hopefully we'll have some discussion around these and other topics today. These are the list of speakers. I'm going to take them in hopefully in the order listed here, and I'm just going to introduce them one at a time as we go through. But I want to emphasize as well that this is intended to be interactive. So we want your questions. Please put your questions in the Q&A tab, and we will try to get those. The way we're going to do this is each speaker we've asked to give roughly a 5-minute kind of opening remarks, and then I have some questions already prepared that I'll ask the panel members, and then we'll keep an eye out for your questions, and again, really encourage you to participate and to make this as interactive as possible. So with that, I will stop sharing and go back to the session.
Feel like the Brady.
Okay, it looks like we've got our panel members lined up. So what I'm going to do is first introduce Amber Andriaco, who currently leads the GE Additive Materials and Process team, which is focused on laser and binder jet modalities. Amber joined GE Additive in 2017 as a principal engineer for materials behavior, leading several initiatives for AM characterization, focusing on mechanical testing and analysis methods. She actually started her career at GE Aviation in 2005 as part of the Edison Engineering Development Program. She subsequently joined the Materials Behavior Organization, taking ownership of mechanical property testing and analysis for additive materials, worked extensively on the mechanical characterization of high-temperature single crystal alloys for GE Aviation's next-generation turbine airfoil materials, and was instrumental in updating the company's material design allowable publication system, which enabled access to engineers at various GE Aviation sites around the world. She was promoted to senior engineer in 2013, focused on AM materials for the next generation of engines. She helped to define requirements for AM qualification and cert, and facilitated introducing new methods for evaluating additive materials. Amber holds a Bachelor of Science from Carnegie Mellon and a Master of Science in Materials Science and Engineering from Ohio State. And with that, Amber, I'll ask you to unmute your mic and turn it over to you.
Hi, good afternoon, good morning, wherever you are. I'm happy to be here. As Jim mentioned, I've been in kind of the aviation industry for about 10 years now. And obviously standards and qualification have been near and dear to my daily activities for within that time. I come from an organization where the majority of standards that we were internally created. And so, we always kept an eye, and we have been, especially now moving into additive, want to be extremely engaged with the, broader standards committees to ensure that with the, being an OEM of an additive modalities, we want to make sure that we're engaged and following up and being able to work together so that we can make our customers successful in this. So we also, really try to work with our customer base to get them into production. And, if they aren't used to having internal standards, leveraging these industry standards is, really where we want to be engaged and get the feedback into those communities. So.
Okay, finding my way around the controls here. Thank you, Amber. Next, we're going to go to Blake Marshall. Blake manages research and development programs that advance the state-of-the-art in additive manufacturing technologies for the Advanced Manufacturing Office in the U.S. Department of Energy. These programs aim to increase U.S. manufacturing competitiveness, save energy, and develop novel technologies that meet the cost, rate, and performance requirements of industry. Technical focus areas include directed energy deposition, fused deposition modeling, binder jetting, and large-scale industrial system integration. Blake?
Thank you, Jim, and thanks for having me. Very much look forward to the discussion. I'm going to just quickly give a bit of an overview of what we're doing and the work we're doing in the Advanced Manufacturing Office, the Department of Energy, for those in the community who haven't had a chance to really engage with us on that. And then quickly just give a few observations in terms of the ways in which our work is interfacing, I think, with the standards community, just to help seed some discussion. So as you mentioned, we do fund research and development and additive manufacturing. We have, roughly speaking, a $20 to $40 million portfolio of work in this area per year. And the majority of that work is through the manufacturing demonstration facility at Oak Ridge National Laboratory, which some of you may be familiar with, just to help align the stars on that. So that work is one and the same when I speak to that. In terms of our research focus areas, we work on developing new materials, new feedstock processes for developing those materials, improving processability of existing alloys and tailoring alloys for additive manufacturing and polymer systems as well. We really are targeting additive manufacturing systems at the scale and throughput needed for industry. So that may mean very large scale, very low cost systems for things like tooling, which we see, through the development of like the Cincinnati BAM process. That might also mean very small parts that are a high value for things like injection molding, inserts, and things along those lines. It really depends on the scale and the throughput needs of industry, but really targeting industrial scale development where some other additive, capabilities aren't naturally headed. A lot of our work is leveraging national laboratory capabilities. I mentioned the MDF at Oak Ridge National Laboratory. We use a variety of public-private partnerships, both through MDF and through other mechanisms, to help open up some of the capabilities and the resources that already exist or that are used for basic science and high energy physics and these sort of things to the industrial community and the research community as well. So we have a variety of different programs focused on that, whether it's HPC or neutron imaging, robotics, etc. And we support a lot of new capabilities in additive manufacturing, really generally speaking, just trying to push the state of the art, and the areas we touch on are very diverse as well. Metal powder bed fusion, binder jet, concrete extrusion type technologies. We work on hybrid technologies that integrate additive manufacturing with subtractive capabilities in situ on metallic systems. We work on large scale metals DED systems, polymer composite systems, and also we do work on digital thread or digital factory, digital twin efforts, really looking to position some of the resources that we have to be sort of a national test bed infrastructure, so to speak, to integrate data science approaches with AM systems. So we have a very wide range of research that we do support, and that is supported by standards. So that's kind of in a nutshell what we're doing. To transition to today's discussion, I think the main theme of the perspective I'd like to sort of touch on here is the intersection of I'll say the pure research community with the other various application-based communities that may be looking at additive manufacturing for a more qualification and certification for more higher TRL range, more mature application spaces. How do we connect those two communities whose needs and whose incentives to participate and to inform standards may be slightly different? As I mentioned, we develop the systems, we develop the materials, we do not develop standards. We're not an SDO by any means. We do use standards. We do, we'll often set targets based on known or published standards, or leverage other standards for material systems that aren't additive. But at the end of the day, the researchers and the research that we're doing are not necessarily highly incentivized to get out here and help with the development of new standards. A lot of what we want to, in terms of turning the page on that discussion, the things that I think would be really helpful from the research perspective, with respect to the standards, is really pushing the state of the art in taking our, essentially connecting the computational resources and the modeling efforts with the in situ diagnostics and information gathering systems that we have within the actual processes and the intent data, finding ways to speak common language when we're applying a model that might be applicable to two different systems, two different makes, two different types of approaches, different geometries in situ, different resolutions in space and time, and really pushing towards advanced physics models that can help answer some of the more fundamental needs and performance of these parts. Often the standards don't quite exist at those resolutions and those time frames that really we're looking for, that can really unlock very high performance capabilities in the next generation of equipment. So with that, I will close up, and thanks. I look forward to the discussion.
Thank you, Blake. Move on to Bill Billman, who is founder of Aerolytics, a management consultancy dedicated to aerospace materials manufacturing and the supply chain. He started his career in 1995 as an engineer at Raytheon Aircraft, and over the past 2 years, he has been involved with SAE additive manufacturing standards development. He has a PhD in industrial engineering from Purdue University. His dissertation addressed the impact of AM on the aerospace supply chain. He also has a BS and MS in mechanical engineering from Purdue and an MBA and MPA from Cornell University. Bill is a licensed private pilot and a lifelong aviation enthusiast. Bill?
Thank you, Jim. Wow, the bio always seems so much longer when it's read publicly, so next time I'll be sure to abbreviate. Really, thank you. It's an honor to be here. Thank you to ANSI as well as American Makes for coordinating this. I think that all the panelists are very enthused about being here because we realize the importance of this topic in moving standards forward. So what I'm going to do is I'm going to share my screen here and show a few slides because I have a tendency to ramble. So I think it's in everybody's best interest here. Can you see that? I guess I have to click on this. Bear with me. Okay, success.
There you go, we can see it.
So just a few slides on behalf of SAE International. We'll talk about the additive manufacturing ecosystem. And I'd like to start with a little bit of a timeline that we've been researching this space coming up almost on 20 years now. So there was some earlier research on titanium 6-4 directed energy deposition that involved a number of members in the committee. And at the time, additive didn't really exist, at least the concept. So it fell under Committee G, which manages titanium. And then we received a formal letter from the FAA. It was a tasking letter in 2015 that was the invite into this space. And we soon launched a committee on additive manufacturing. So we've been at this for the last 5 years. It's an important milestone for us, the 5th anniversary. In 2017 was our first guidance document, and then our first standard was issued in 2018. And this really established the framework for additive metals, and we'll talk about there's a polymer work that we started which followed that next year. So in 2019 we started with the repair committee, all dedicated to aerospace, of course, and then the non-metals, and then the launch of what we call the AMDC, the Additive Manufacturing Data Consortium, was this year. So kind of by the numbers, 19 total standards to date, which is pretty impressive because I think the people on the call are very familiar with how long it takes to actually release a standard. There's a lot of work, and that breaks down to 17 metals and then 2 non-metals, and we have almost 30 in process, including 5 revisions, 500 plus members strong, 24 countries. And then this is kind of just to break down. I think we're pretty proud of the fact that we have good representation across the supply chain, starting with materials and then aerospace OEMs. And that includes this whole space tourism, which is kind of an interesting market, but also machine OEMs, the different members in the tier supply chain. So very diversified and well balanced. And then kind of the aerospace pedigree, because we have a tendency, if I was a project engineer back at Raytheon, the FAA takes part pedigree very, very seriously. You have to actually certify not only the material, but the process. That's part of the reason why additive manufacturing is so nuanced. It's process intensive. But this goes through this whole progression of using data to create these spec minimums, and then ultimately what we want to do long term is develop design allowable database. And we've had a relationship now with Battelle that goes back to the 70s with regards to MMPDS. And that's what we want as engineers. We want to minimize the uncertainty. And then lastly, kind of our foray into that space to help provide the fundamental lack of data, that pedigree data, is the formation of the AMDC. That, again, was announced this year. We're in the process of formally announcing that, making that public here within the next week. And it's really the symbiotic relationship between the standards and data generation, and then that's upstream, of course, and then downstream are some other SAE family products, pre NADCAP that have to do with supplier registry, so part of the ecosystem. So with that, I would like to say thank you, and we'll take questions, I guess, later.
Okay, thank you, Bill. Next, we will move on to Kate Hyatt, who is a project engineering manager at the American Society of Mechanical Engineers, ASME, in the Standards and Certification Department. She has over 15 years experience in the development of ASME standards in a variety of areas. In her role at ASME, she enjoys working with diverse teams and developing standards, guidance documents, and events with the end goal to improve the quality of life, increase safety, and inform the world of engineering advancements. Her current projects are focused on the areas of big data, manufacturing, additive manufacturing, and verification and validation of computational modeling and simulation. She's also responsible for international outreach and collaboration with nuclear standard volunteers in Asia. Prior to working at ASME, she was a design engineer for Bechtel Power, responsible for mechanical systems for natural gas and coal-fired power plants. Kate?
Thank you, Jim. I appreciate the opportunity to be here and to speak with all of you, and hopefully you can see my screen. I do have a number of slides. I'd like to take the opportunity to really talk about what ASME is currently doing in the additive manufacturing space. And most of this relates to the standardization roadmap that Jim gave the preview of during the initial part of this discussion. So ASME has a number of new standards activities related to additive manufacturing under development. This slide kind of provides a snapshot of those areas, and I'm just going to give a brief overview of some of these topics in the next few slides in hopes that that will inform some of the conversations that we have after these introductions. So we have our ASME Y14 committee is our engineering product definition and related documentation practices committee. It has recently added a number of model-based definition standards that can be utilized to support additive manufacturing design, such as the Y1441 standard, which establishes requirements for digital product definition data, such as data sets or graphic sheets. Y1446 establishes definitions of terms and features unique to additive manufacturing. This needed to be created to capture all of the dimensional intricacies that are now available to us in additive manufacturing. Y1447 standardizes the exchange of 3D model data used to determine an item for manufacturing and procurement. And Y1448 is in development. It will be addressing build direction in additive manufactured parts, direction of fibers and composite parts, direction of geometric tolerance zones, and the direction of surface texture requirements and other specifications. We also have our B46 document, which is been around for a very long time. It defines surface texture and its constituents, roughness, waviness, and lay. Now, recognizing that the current measurement and analysis methods were developed primarily to characterize surfaces created by conventional machining and grinding, and that those surfaces created by additive manufacturing have distinctly different geometric characteristics, additions were made to this document in Appendix B to cover references to standard AM terminology, handling issues from cracks and porosity, and providing cautionary statements on limited knowledge base and wide range of AM standards and materials. There's also a new Appendix K that provides suggested terminology and procedures for evaluation of functional correlations of surface textures with processing and performance. That was just issued in June 2020. Another new standard that was just issued is our B89.4.23. And this standard specifies a dimensional measurement accuracy of X-ray computed tomography systems for point-to-point length measurements of homogeneous materials. It was just issued in November. Now, this is actually the standard that I feel is most relevant to today's discussion. We have a joint board on pressure technology and board on nuclear standard codes and standards committee that has been developing a guideline document on criteria for pressure retaining metallic components using additive manufacturing. This document is providing guidance on the essential elements to be addressed by any standard for the construction of metallic pressure retaining equipment using laser and electron beam powder bed fusion processes. It's intended as a reference document for proposals for construction of AM pressure vessel equipment, kind of code cases that would be brought before our board on our boiler pressure vessel codes to gain approval for construction processes. And in it, it provides guidance on design, process variables for qualification, AM procedure qualification, qualification testing, and production build testing. So I think that'll be key for that industry to provide that type of guidance. And we have a few more standards committees that have developed over the last just couple years. Our first one that I'll just mention briefly, our first one is our Manufacturing Standards Committee formed a new subcommittee on additive manufacturing. And this group will really be focusing on areas that have been identified as remaining gaps in the American Make Standards Collaboration, that's standardization roadmap. We also have a new industry-driven standards committee aimed to develop guidelines and standards for bioprinters, hardware, and requirements. This document will provide guidelines for extrusion bioprinting, the calibration of the device, operations, compatibility, and interoperability of these components to provide ex vivo tissue results. And the last two activities that have really gotten moving in the last couple of years are our model-based enterprise. This was a natural extension of our Y14 activities, and this group aims to develop standards that address the use of a model from the concept through design, manufacturing, inspection to customer feedback and retirement. And our Manufacturing Standards Committee also has a subcommittee on monitoring, diagnostics, and prognostics for manufacturing operations. That group is looking to address measurement, recording, and monitoring equipment deviation from normal operations and predicting the reliability of a product or process. That group will most likely be forming a new subcommittee or subgroup to look at specific requirements for additive manufacturing. So those are some of the areas that we are currently working on, and these slides will be available to all attendees after this event. If you have any questions, I've included some additional materials here, and I look forward to this discussion.
Thank you very much, Kate. Next, we have Dr. Hallie Deutschman. She is a research group head at Siemens Corporate Technology. She completed her PhD in materials science and engineering at Ohio State University, studying nickel-based superalloys. Before joining Siemens, she was heavily involved in additive manufacturing for aerospace applications, working in advanced materials group for AM at Honeywell Aerospace, and as the principal technologist for advanced manufacturing and materials at Blue Origin. Dr. Deutschman was also a founding member of the SAE AMS Additive Manufacturing Committee and the current committee secretary. Hallie?
Thanks, Jim. I had some slides prepared, but in the interest of getting us straight to the panel discussion, I'll just do a brief overview of Siemens and additive. So for those of you who don't know, Siemens is a massive corporation. We do a little bit of everything from NX software, which a lot of engineers use all over the world, to back-end controls for additive OEMs, all the way to trains through Siemens Mobility, energy generation, Siemens Energy, and healthcare tools for Siemens Healthineers. So I work for Siemens Corporate Technology, which is the global R&D arm for Siemens, which means we get to work with a lot of people. As far as standards in corporate, I see our role as fivefold. The first is that it is my responsibility in corporate technologies to keep an eye out for standards that then become flowed into our business units for their use. The second is to keep an eye out for the standards so that I understand where cutting edge is going and where industry is going, also to guide our business units. So because of that, I'm heavily involved in the group that Bill mentioned, SAE Additive, as well as members of my team are involved in other committees as well. Specifically, my group focuses on component manufacturing and inspection technologies. So we are the intersection of physical and digital, headquartered in the US. We have a facility in Charlotte where we actually are honored guests of Siemens Energy. So we are a corporate lab on an actual business unit site, which means we have an interesting view into how energy sees standards, as well as how we can flow R&D out to the rest of the company. And then I'll finish and get to the panel.
Short and sweet. Thank you, Hallie. So we'll move on to Shane Collins, who is currently VP of Additive Industries of North America and the General Manager of the Process and Application Development Center in Camarillo, California. He's responsible for sales, marketing, service, and applications development for North America. Shane is a 20-year veteran of the additive manufacturing industry, holding various positions in product management, business development, and operations for both 3D printing machine manufacturers and Tier 1 part suppliers in both polymers and metals. He sponsored several metal powder-based fusion standards and holds the position of chair of the ASTM F4207 on AM applications, and formerly for 10 years was chair of F4205 on materials and process. Shane was presented the ASTM Robert F. Painter Memorial Award in 2017, the ASTM Award of Merit in 2018, and has the honorary title of Fellow. He's co-author on publications in the powder bed fusion of 17-4 stainless steel, nickel alloy 625, nickel alloy 718, and aluminum alloy C360. Shane graduated from Purdue University in 1980 with a BS in management. Shane.
Thanks, Jim. Good to see a Big Ten theme going on here from all the panel participants. That's good to see. I'm going to share a few slides and in 5 minutes bring everyone up to date what ASTM has been up to for about the last 12 years. So bear with me here. So the F4207 that I chair is one of the subcommittees within F42 where we have the different sides of standardization for the test methods for the material and process, which is F4205, where I chaired for about 10 years. And now under F4207, we have looked at standards development a little bit differently, going in by application, because we find that each one of these different areas of industry use standards a little bit differently and have different needs when it comes to standards development. So F420701, which is on aviation, and 02 on space flight, those are very closely related to the whole thing on aviation and standards development. And then we have the medical 03, transportation, maritime, electronics, and what I think will become the largest area of standards development will be the 07 on construction, when we talk about 3D printing concrete and making domiciles and other bridges and structures. And then we have oil and gas, and then consumer products.
Hey Shane, yeah. Sorry to interrupt. We're not seeing, or at least I'm not seeing your screen. So I don't know if there's.
That's unfortunate because it worked in the beginning.
Hey Shane, leave it to the Purdue grads not to be able to figure out this software. So
there we go.
Now it's working.
You're on.
Yes.
Okay, great.
Yeah. So I have to switch screens because the way this works on my MacBook, and it was telling me that I needed to accept this or whatever. Okay, so this was the nice graphic that you missed, talking about applications and the different areas in which the F4207 is developing standards. I put this slide up because I wanted to show that there are many organizations that are using additive manufacturing, particularly powder bed fusion, to make flight critical, safety critical, performance critical hardware. And that's a picture of a satellite bus being put together with carbon fiber and titanium printed parts. This is one of the, just an example of one of the many specifications that the companies are using in the past. And And to have worked under these specifications, it allows some of the ideas and concepts behind what the primes and the tier 1 suppliers are looking for in the process controls and other parts of it. ASTM has a lot of collaborations, not only with F42, but other committees within the ASTM community. The E07 on NDT, the F04 is the medical device, the B09 on powders, and then the relationship that Jim talked about between F42 and TC261 and ISO. We have the TC44 folks on welding, which recently passed a very, I think, groundbreaking standards, which is the 52941 document, which is the calibration of systems for aerospace. So it's very important. And then there's the TC150, which is on implants for surgery. That's on the ISO side. And then we have other collaborations that are between F42 and these other organizations, so that we make sure that we're developing the right standards for the right applications. And we've had the America Makes Memo of Understanding since 2013, the different government agencies of NIST, NASA, FDA, FAA, et cetera. And then if you remember on Jim's example that he gave of a gap, there was a section that said research required. And that's really important concept, because a lot of the standards that we're trying to develop in additive manufacturing, we need some data or we need some research tools in order to be able to write standards that are hitting the mark. And the Center of Excellence was created in ASTM to provide fundamental research, not in general of additive manufacturing, but related specifically to finding the information necessary to complete standards. So that partnership is EWI, MTC, AU, NIAR, NASA, NAMIC, and then the different certification bodies, a Memo of Understanding with UL and the TUV SUIT and other SDOs that we have relationships with. Well, this is an eye chart, but it shows all the standards in F42 that have been passed so far, and it's been categorized by the terminology, the methods, materials and process, test methods, and goes through. It would take quite some time to dig into each one of these to figure out what they're doing. So on my whiteboard, I put together sort of a chart as to if I have a quality system like an AS9100 or a 13485, how do I take the ASTM ISO standards that have been passed so far and apply them to my quality system? And so once I put that on the whiteboard, then ASTM was able to take this and really bring it to bear where the standards exist and the work items are under development. And you can see that all aspects of the process for laser powder bed fusion, electron beam powder bed fusion, have some aspect of a work item or an ASTM standard already that has been passed. So this is a body of work that has taken about 12 years. And finally, my last slide, I wanted to talk about a little bit how we're thinking of part qualification now. Some of you might know Charles Park. He's responsible for getting parts certified on the Boeing commercial side. And he has put together sort of a concept of qualification with additive manufacturing, particularly metal, where in the past we had this idea of standards and specifications, both internal and external, from the SDOs and the company's internal. Then we create this design allowables database, either public or within our own organization. And then we go into process and part qualification. And we're taking a little bit different path, I think, going forward, because one of the things that's missing in that is the whole idea behind design practice and part criticality. And that's going to be important driver for, does the business case for that make sense? What is the maturity of the technology and the intent of the part itself? And then that will create a certification path that will drive the NDE and final inspection criteria. So looking at it from a different perspective rather than the traditional design allowable, part qualification, standards and specs. So that I think is probably where we're headed as a F4207 organization. And with that, I look forward to a good discussion on the panel.
Terrific. Thank you, Shane. So it looks like we have about a full hour here for some discussion. And again, there is, my understanding is folks can add questions to the Q&A module in your console, and we'll try to get to those. I'm going to start off with just a couple here, maybe circle back to Amber. Amber, what do you see as the gaps in industry specifications that need to be considered, particularly when implementing for production hardware?
Yeah, so I'm coming from this from a materials perspective, and I'll maybe give two examples that I've come across with the industry specifications, and I'll start with feedstock, right? So feedstock, I think, you know, the specification organizations are doing a great job putting around the framework in place for the powder and the feedstock specifications. What I think, you know, we need to understand is some of those feedstock specifications, and I'll use the powder as an example, you know, they're currently listing the typical things that you would have seen in those specifications: the chemistry, the particle size distribution, you know, some other density characteristics potentially. And I think what, you know, we've encountered personally, and what we've heard feedback from customers is, you know, not all powder is created equal, right? So even if you get a powder that meets that entire specification, it may not result in the same capability coming out of the, you know, additive machines. And so I think there's that recognition that we need to figure out, are we missing characteristics in the powder, or can we better define requirements in those specifications to drive more consistency across the different manufacturers, and then ultimately drive that consistency into the parts being produced. The other example that I've come across, and actually during our ASTM consortium meeting yesterday, I brought up was, you know, there's a lot of companies, because they've been so used to using industry standards and having the backing data, material allowable data to go with those, you know, the values listed in there, and I'll use tensile as an example, the assumption is that's truth, right? In my process, as long as my value or my tensile bar coming off my build platform is meeting that specification value, then I'm all good. And what I always, you know, caution our customers that maybe you're thinking along that lines is, okay, well, you really need to understand, what is your process giving you? Because what if the value in the specification represents a -6S versus your overall process capability? And how does that, again, relate to your design allowables? So I think, you know, just education, more education. I think, you know, as a couple of the panelists have said, you know, coming to a common agreement on not only language, but the data, and being transparent with what's going into those data, those specifications from a data perspective, I think can help close some of those gaps as we move forward into trying to make this more of an industrial process.
Okay, great. And I guess just in terms of process here, you know, if any of the other panelists want to weigh in on any of these questions as we're going through, some have more general application, just give me a raised hand signal or whatever, or unmute yourself, and I'll call on you or put you on the stack. Let me just sort of maybe look at this a little bit from the R&D perspective. So, and this is really maybe a question more for Blake, but when we talk about AM standards for production and reliability, that those may be different than standards used for the research community in terms of pursuing novel capabilities. how might we more closely link the needs of the production and research communities through AM standards?
Thanks, Jim. Yeah, great question. So I think I noted a bit of an intro in my intro. Incentives, I think, that you see between the different communities, and I think especially with respect to the way we use the way you might see standards used in a research program. I'll just kind of quickly talk to that and then transition. Often, standards that exist provide a very good pathway to follow in order to reduce the uncertainty of the things that you don't want to be a part of your new capability, for instance. So we might say, relying on safe powder handling specs and material testing specifications for coupons and all these sort of things are certainly highly valuable to the research community, but they're taken as is. However, to unlock the next generation of capability within these additive systems, there's a lot more, like I mentioned earlier, very fine details of spatial resolution, time resolution, things we really need to understand a lot more information on that current standards that are more applicable for not the conventional processing don't quite apply. So, standards are not ever, their role is not to lead research and development. So that's all fine and good. I think the question comes down to what can we do while we're currently doing research to help feed future standards, I think is probably, for me, kind of a sweet spot. And I don't have an answer to that question, but I think that's a good area for discussion for groups like this. And maybe that's just which sort of data protocols we're going into before we start that research project. Maybe it is what types of data, in situ process data, are you keeping and storing? It might be data truncation technologies. It could be a whole wide range of things. But with the understanding that the next generation of standards is going to have to be more and more integrated with much finer spatial resolutions and integrated with computational resources, all throughout. But the standards both drive the way in terms of what we already know, certainly, and then the question mark for me is how exactly do we feed back towards the standards community as we're actually developing new capabilities. Thanks.
Okay. I see a couple hands. Hallie, do you want to go next, and then Bill?
Sure. So just sort of following on what Blake had mentioned, it's good to use the standards as a baseline to understand what is going on with industry and then use it to identify gaps. The other thing is having people on the R&D side involved in the standards, knowing that they, at the end of the day, are really guidance documents. They're not prescriptive, at least from external SDOs. And having R&D people involved in the community and seeing what's going on and looking for those gaps and then bringing it home, I guess is the best way to put it, to then leverage the next generation, I think is a powerful way to sort of keep driving advancement and understanding.
Okay. And Bill?
Well, just very quickly, it's you don't know what you don't know, and I think as I'm a strategic management consultant, and I spend a lot of time thinking about that. The role of standards is to provide guidance, and in particular, whom are we informing? And it's really the supply chain. So because the large companies aren't going to share their secret sauce, if you will, with the world, so that makes sense. It's considered intellectual property and it's protected. But if a company's perfected this and then they don't share, they don't disseminate that, then the industry stagnates. Because I'll give you an example. A typical aero engine, even the aircraft, about 80% of it's built externally by the supply chain. So it's really the role of the OEM is on the behalf of systems integration. So if you think that they're focused on just 20% of the manufacturing and assembly, then they're going to rely heavily on the supply chain. And lastly, for example, Boeing has 13,000 qualified suppliers. So how do you orchestrate and organize? So I think that's the importance role of the standards is taking some of that's particular to the organization and sharing that with the supply chain so we can enable that as much as possible. So but it's hard. It's a snapshot in time, and it also takes a consensus to reach a decision. So it's very challenging.
Sure. So we're starting to get some questions in the Q&A, and that's great. And I guess there's a feature you can upvote them. Some of them are more general, some of them are a little more specific. And some of them relate, I guess, directly to the work of the SDOs and or to the AMSC. Shane, you talked a little bit about this in your opening remarks, but you want to just touch again, since we've been talking about research, like how the AMSC roadmap has impacted standards development?
Sure. If you look at the research going on the COE, and now I believe we're in our third year of project calls with the COE, in order for a project to go forward, they had to identify where on the ASMC there was a blocking issue that needed resolution. So from the ASTM standpoint, and particularly the COE, the ASMC document has been the Bible by which we determine what used to go forward. And I think you'll find that there were many of the ASTM folks that were helping to put together the ASMC roadmap, and because we realized that there were a lot of gaps involved, and those gaps needed to be filled. And how do we fill those as soon as possible? The best way is to get consensus from the community on what we needed to address and in what priority. So it really, as the SDOs are composed of a free labor force, we are all volunteers, and we also have our various day jobs, as you've heard everyone talk about. So our standards development happens on the extra time and on the weekends, and we tend to use self-fulfilling needs fulfillment when it comes to standards work. So you have a supply chain, you have a particular process that's coming up, you need this standard to be developed, you apply some resources to get it done so that you can have a really good transaction with the supply chain, and that is a need that gets filled. And that's the way standards development tend to roll out. But with ASMC now, we have a priority list that we can attack more precisely and with a focus. And that's where it has been a great document for us. So we're very supportive of that on all of the ASTM subcommittees, and especially the ASTM COE.
Great, thanks, Shane. So I want to just keep it at a high level still. We've got some very deep dive questions here. The couple about the roadmap. There's one, is there a version 3 planned? That's under discussion between America Makes and ANSI. How can I support this? Are there committees? Who should I contact? Well, certainly, I gather we're going to share the slides, so you have contact details, for SAE, ASME, ASTM, in terms of getting directly involved. And again, the roadmap, sort of elaborates further on the different types of activities that people are involved in. I want to talk just a little bit more. I mean, I started out at the beginning talking about how certainly the roadmap, I think, was reflective of the fact that there is heavy pickup of the technology within the aerospace, defense, and medical sectors. But what are you guys seeing now? And this is really for anybody who wants to jump in. I mean, Shane, you have the F4207 that has the different application areas. What are folks seeing in terms of which sectors are really starting to get more, or to embrace more AM? Let's start with that one, if anybody cares to take a stab at that.
Shane, you see across sectors. Oh.
Let's go Hallie and then Bill.
I'm seeing a big push in energy, partially because there are a lot of overlap in technologies and material systems between aeroderivative engines and energy generating engines. So it's a nice way to take the work that's been done for propulsion engines and sort of take what's needed and distill it down for guidance for energy generating engines as well.
Good to hear. Energy. Bill? Did you?
Actually, I was deferring to Shane because he sees across these verticals. Just quickly, I see a lot of activity in medical. the customization, the strikers and the Zimmer Biomets of the world for hip cups, for example. In aerospace, there's a big push for MRO, maintenance, repair, and overhaul. 70% of the budget in military is sustainment, and that's in the billions. And so there's a lot of work in that area, especially for something that we don't necessarily look for, the gas turbine per se, but turning aluminum. But then obviously in aerospace, the concentration that I see is not really in the airframe. Airframe looks more at titanium directed energy deposition, and then for the gas turbines, we're looking at powder bed fusion. A lot of Inconel 718 and Esploy. So, but yeah, I think right now that the aviation is lagging, as everybody knows. Anybody close to that industry, it's been just a disastrous year. So the activities that I've seen, a little bit of energy, and then also.
So I would echo what Bill said about MRO as a bright spot for additive, all the various types of additive polymers as well as metal. There are some challenges with that in terms of material substitutions, and we're trying to figure out how to make that work. But that cuts across the various verticals. It's aerospace, it's oil and gas. For us, we take energy, we put it oil and gas, and then there's maritime. And the ability to print spare parts on demand, particularly what I'm talking about is casting replacements, where the castings are hard to come by nowadays. And I think you'll see that become a very big push. On the medical side, we're starting to see what the new thing is, trying to figure out how we deal with this point of care type 3D printing and additive manufacturing, whether it's in the hospital or a building adjacent to the hospital, and how do you create standards and have safe devices that are produced in that environment. So those are, I think, some areas outside of the where you don't think of 3D printing, of making houses and buildings. What's going on right now with 3D printing concrete, both for military applications as well as maybe space and third world country domiciles, is really it's an amazingly fast pace what's going on. And so if you just go to your local box store for your, like a Lowe's or Home Depot, and you see all of the standards that have been passed for all those building materials, whether it's pipe or if it's a faucet or whatever, we are going to need some element of that for additive manufacturing, because everything that's in that box store will have some part of it that will be used through an additive process. So from where I see now, we've had a lot of impact on aviation and space with standards. That's because the parts have been so expensive so far that only those industries can afford to use the parts. But now we're seeing efficiencies of the 3D printing devices driving the part costs to a level that we're seeing adoption across the masses, and that's going to open up standards development opportunities in a lot of different ways. So if somebody wants to get involved, certainly right now we have a very good opportunity to do that.
Thank you. Amber, you wanted to weigh in?
I think I agree, especially the MRO comment. I'll say from our perspective, I've seen a bit of an uptick in the automotive and kind of transportation area too. You know, and kind of along the lines of one of the questions, you know, yes, powder bed fusion has been one of the biggest ones that have had standards, and you know, one of the technologies and modalities I think automotive is really drawn to right now is like binder jet technology for that mass production space. And so there was recently, I believe, the process specification for binder jet was issued through I believe the AMS SAE organization. So, you know, that's, you know, it's not, I would say, fully adopted by the masses, but I think we're starting to see a bit more interest in there, and they're trying to also build off of a lot of what the aerospace industry had really established, and taking some of that and driving that into, you know, the casting replacements and whatnot for the automotive industry.
Blake, did you?
Yeah, just wanted to second some of the other comments, as well as add a little bit additional context for the energy markets. As Haley mentioned, we're definitely seeing a lot of uptick or interest with respect to, I guess you'd say, traditional generation, like gas turbine systems. And we've had some recent successes in that area, certainly seeing that capability being used there. But I would also point out there's quite a bit of a diversity of uses of additive within the energy sectors in general. Certainly seeing a lot more nuclear applications for small modular reactors, which is driving some standards development that's very specific to that field of use, but certainly relevant to the community here. We see a wide range of different processes playing into that as well. I mean, powder bed fusion tends to be the unspoken leader in terms of talking about this, but the concrete printing, for instance, what Shane mentioned, there are energy applications there, both in terms of, we could talk wind towers. You can actually, within built systems, built environments, we can actually look at energy efficiency and have dramatic improvements in those spaces. So there are various typically smaller companies and things, but working towards those application spaces. And there's one area that I think I would agree with Amber on automotive as well, especially with respect to binder jet technology. But one area that doesn't get as much discussion is actually tooling uses within the directly within the shop itself. So there's a lot of work there in terms of, and there is, it's not directly energy, but there is an energy angle to that as well. But printing forms for composite layups, printing a wide variety of things within the shop floor. Tooling itself is a very major area that is just growing and certainly something we're targeting.
Okay, let me come back to that, just the different processes, but I want to give Kate an opportunity. What are you guys seeing at ASME in terms of representation from different industry sectors?
Right, just to echo a lot of the things that all of the speakers have said, within the energy systems, as Blake just mentioned, the nuclear applications is one of the drivers for that guideline document that we have on criteria for pressure retaining metallic components. And we see that being applied to the SMRs as well as traditionally manufactured nuclear components, especially for legacy power plants where, original drawings and original manufacturing techniques may not be available and you need to do replacement parts. So that's definitely a use for that. The other thing we're seeing, in addition in the medical space to your medical devices, is we do have this new standards committee that was just developed on bioprinting actual human tissue. So that's a whole new area that we didn't foresee a couple of years ago, but there is definitely a need, and that's an industry-driven area that we're working on right now.
So for someone who's coming into this for the first time and trying to figure out where to participate, are the standards development processes the same, or do they vary across the different industry sectors? Does anybody want to sort of weigh in on that, and how, in terms of how you would provide guidance to somebody, where they want to participate?
From my perspective, it's what are you interested in? What's your area of expertise? We have a certain number of activities. I've kind of given a brief overview today of what we're working on, and anyone is welcome and who's willing and able to participate on our standards development committees. We're also, all of our standards are really industry driven. So if there's a need out there that someone would like to address that isn't being addressed elsewhere, we are using the standardization roadmap that AMSC has developed to make sure that we're not, stepping on each other's toes, but we are open to looking into new areas if there's a need. I'm sure Shane has some other.
Yeah, I was going to say, I know there's some slight differences in terms of SAE's approach and maybe ASTM. Either any of you guys involved in either of those want to speak to what some of those differences might be in the approach to standards development?
Within the way to get involved in ASTM F42 or ISO TC 261, which are a little bit different. And ISO has country experts, and every country has 2 experts that get assigned. Whereas with ASTM, anyone can join any of the subcommittees or work items. So the best way to get involved would be to go to the ASTM F42 website, and you can pull up a list of all the work items that are under development. But what I would prefer is that you already write a standard, or at least a document that has an outline of a standard you'd like to see passed, and you bring it to us, and then we can figure out what subcommittee it would be best delivered in, and then we can, so what we need are not only people that want to join committees, but also we need proactive folks who are willing to be the technical contact for these work items, because it is a lot of work. Not just writing the document is about half the problem or the time concerned. When you start going to ballot and you get a lot of comments and negatives, and you have to figure out how to mitigate those and how to modify the document and horse trade, different types of specs to make sure that everyone can vote affirmative, because one negative vote stops the process in the ASTM and ISO format. So one negative vote out of the 1,500 or so members of F42. So you have to get 100% consensus. That's not easy to do. And so that's why it's really important to have a really good motivation and not just want to join so that you can monitor what's going on, but actually be a proactive member. But I think SAE may be slightly different or similar in those ways. Bill?
Yeah, Bill or Hallie, do you want to?
Yeah. Well, yeah, Holly's a great point of reference. I'll just add that in a couple things in SAE, the individuals are members. So it's not your company that joins, and it's a very interesting kind of esprit de corps. There's people that have been doing this for many years, decades, and are very ardent supporters of SAE and the type of work. And I think Shane articulated it well, that it's really self-fulfilling in a sense that you have to be vested in the process, because it requires a lot. We have close to 600, I said above 500, it's close to 600 members. And there's, of course, varying levels of participation, but really, I think the point that Shane made was really central to the fact that we need sponsors. And so the whole idea of a standard is born out of a need, and we're very market focused, but at the same time, you have limited resources and you have to plan. So just because big issue to a company, whether or not we can get a consensus around that is a whole other issue, because if not, then you need, it's an army of volunteers, so you need the individuals to be able to rally around that particular topic, number one. And then number two, you need to be disabused of any one particular notion of a company perspective. So I think that's the other thing that we try to do, is harmonize within the organization, like powder recycling, for example. One manufacturer might have a different perspective than another, so we want to make sure there's no bias in the process. But in terms of getting involved as a volunteer, it's free. It's free to join. It's an open door, but there is a hope or an expectation that the individuals contribute.
Okay, great. There's some questions here. Let's get a little bit more maybe into the weeds. Are all of the standards work based on powder bed fusion? What is happening in terms of the other processes, or are they not far along enough in terms of standardization? Anybody want to take a go at that? Hallie?
Sure. So SAE, well, we did start with powder bed fusion. We've now branched out into binder jetting, as well as more directed energy deposition processes, be they wire arc or powder feedstock. So we are starting to branch out, but as Bill, Shane, and Kate have mentioned, it's really driven by industry. So if a volunteer comes to us and says, we use this process, or we want to use this process and we need a standard, then pretty much every SDO is going to say, come on in, we'd love to hear about your technology and let's see what we can do with it. So we are broadening that spectrum right now.
Yes, Bill?
I just want to add, maybe another question is, why is there so much energy around powder bed fusion? And it's the whole notion, I think, can be summarized in two positions: either design for additive, you make that ship in the bottle, or you do something that you couldn't conventionally, or this whole notion of maintenance, repair, and overhaul, and you don't have the time or the budget to make tooling. And so you want to make some of these parts one-off. So those are the kind of the two corner cases in the business case. But additive manufacturing for powder bed, you can build these very nuanced structures that you couldn't historically. And the reason it's so popular in aerospace is because of the imperative for weight. So that's kind of why metal additive, titanium in particular, but also ink and all, but powder-based fusion is probably 80% of the total market. But directed energy is coming along, and as Holly said, binder jetting.
Anybody else want to speak to the sort of level of maturity of the different processes being standardized?
Well, I would add to what Bill said with respect to powder bed fusion, particularly powder bed fusion could be both polymer and metal, right? So metal powder bed fusion is electron beam laser based right now with the current technology. Those are so far along because in metallics, typically you find more structural and fatigue critical parts than you do on the plastic side. So the needs for standards are probably driven by the application of the part itself, where if you're doing a plastic duct or a clip or bracket, you may not be as concerned about part criticality in that case. So then the question would be, why the difference between powder bed and directed energy deposition? Why don't we have more standardization on the DED side? Because certainly that also has applications there. And there have been a number of ASTM standards on DED. We have a guide to DED that's, I think, about 60 or 70 pages. But there are, as far as the standards for the material, the consolidated material, and what those material properties are supposed to be, we have companies who are making those kinds of parts. We have the highly advertised Boeing. So these are titanium brackets that are holding up walls inside the aircraft that are made by DED process. Those are using internal standards and existing standards to make it. Typically, DED parts are machined on all the surfaces. So what you have is largely a part that's not so much different than a wrought material when you're finished. And I think that's the biggest difference, although you could talk about making lattice structures and all the different internal channels and geometries that you can do with powder bed that make it a unique process and need for more standards. But I think it's because powder bed has found its way into potential safety critical applications that has driven more standards needs sooner than later.
Speaking of DED, there is a question here about laser-based DED is close to classic welding, or maybe closer than powder bed fusion. Do you think standards from classic welding can be used for DED in the future?
Well, let me just quickly add on to that. Yes, I do think that we can learn a lot from the welding community when it comes to both powder bed fusion and directed energy deposition. The ideas behind different gases to create different end product are certainly important for that, and we can learn a lot from what the welding community have done. One of the, if you look at the ISO ASTM 52941 document, which came originally out of the ISO TC44 welding community, when I joined that group, I was like, so they wanted to make sure that all the powder bed fusion machine operators had an eye exam, and this is something that you would normally get from the classic welding side. But I never thought of it in terms of that, because I've had a lot of my machine operators never have an eye exam, but they said, well, do they have to to look at the visual inspection of the part when it's finished and have an inspection reject criteria. And I said, sure, when the part comes out, everybody looks at it to see if it's a good part. Well, then obviously you need to have an eye exam. So that's just one small example where I think the grabbing from the welding community really makes sense for a lot of the metal processes.
Bill, you wanted to, or Blake, go ahead and then Bill.
Yeah, I just wanted to add on to that, I think the answer is there's definitely a strong yes in there with respect to powder DED, but also wire-fed DED. And we're actually doing a lot of work in that space or starting to. And like for just one example of an area that can be directly leveraged is the whole feedstock development side of that. So there's certainly a wide range of wire materials available, for instance, that rely heavily on existing standards, and those standards are very, very useful. There are certainly other examples where there are limits to how far the current standards will help, but there certainly are, and I would say maybe even especially with respect to the wire side of it and arc welding, which is a very mature technology.
Bill?
Yeah, just to add on to that. So if you look at the AMS 4999 spec, it was based on welding criteria back in 2002 with Pi 6.4. I think the second point is American Welding Society. The D20 document is excellent. It's very deep, especially for directed energy deposition for wire. I think that the danger is melt pool characterization when you try to look at laser powder bed, because a lot of that energy is reflected. So really the important process or question is how much of that energy is absorbed, and trying to characterize that melt pool is not trivial. And I think that just anecdotally, the head of our committee, Dave Abbott, studied welding engineering, get more Big Ten, but at Ohio State. So I think there's a natural fit into welding, and I think we could do a better job at leveraging some of that, because like many things, it's noting not only the similarities but the differences, because some of those nuances could be fundamentally different.
Bill, one thing you might not know, the 4999 spec about the Aeromat process, there's a famous picture of a guy on a platform of the Aeromat machine.
Yeah.
That's Dave Abbott.
Oh, is there? Oh, I didn't know
Yes.
that. That's good.
Yeah.
And those of you who have worked with Dave, Holly's worked with him for a long time. He's an engineer. He's good at what he does. He gets excited about it. He spent time at GE Additive as well, and I think that's what we need. We need that type of personality and willingness to share, disseminate that. He's done a good job at kind of leading us. So, but he loves it. He loves what he does. He's good at it.
I want to be as inclusive as possible here, and recognizing I'm not sure of the demographics of the audience, but just take us back to a little bit of a higher level, and maybe we can hear from some of the industry folks. When you hear the word process control, what considerations do you think about, and what would you say is the most important gap in terms of AM process control? Maybe Amber, do you have a view on that, or Hallie?
Yeah, I'll go first. For me, it's certainly with additive, and again, kind of working with customers, when we talk process control, everyone thinks about process control as just the process control within the machine, right? And I am always a big proponent to say, think about the fact that the job, your material is not fully finished usually in additive until it's gone through additional post-processing steps, albeit taking it off the platform or submitting it for HIP and final heat treat. So for me, I think there's a lot of focus on the process control in the machine, and as there should be. But I think, the industry standards and whatnot, there's all those subsequent standards that exist to address, heat treating and, post-processing machining and things like that. So understanding that it's not just the machine and an overall process for AM needs to be taken into consideration, and figuring out how all those standards can then intertwine and come up with that full process. And Hallie, if you...
Yeah, absolutely. What Amber said, we're both M&P people, so we obviously go right to the quality of the material. But there's a few things to consider. The first is additive is really the first time that engine OEMs or automotive OEMs or any OEM has had the manufacturing process in-house, that they're able to see everything where all the bodies are buried and the skeletons are hidden, instead of relying on a robust supply chain that's developed the process. So we're in this unique position now as OEMs where we have to be cognizant of the fact that we can see everything and cognizant of the fact that we don't quite know what to do with it yet. We're also going through this at a stage where technology is incredible, where we can digitalize and bring this brand new technology of additive and see it through the guise of a 21st century person, right? Looking at all of the digital opportunity that we have to sort of look for patterns and trends and use that to drive decisions and control. So I think that's sort of unique as well.
Bill? Okay, Bill's passing out.
You go first.
Thank you. Very gracious. So I think when I hear limitations in process control, one thing that comes to mind is, again, looking to the future for the most part in research and development, really having robust standards protocols essentially for feedback loops within the systems themselves that are linking the in situ process data to some sort of modeling and simulation, or some sort of computational capability, a variety of different ones, back to the process of the actual G code or whatever that's running the actual machine, and making those on the fly adjustments, I think is a very big gap, and it's not a monolithic thing. Those computational resources may take the form of various different controllers, various different ICs and whatnot, actually integrated within the systems. All of those have their own protocol and IO and et cetera to work with. And then of course, however that code is being sliced and generated and pushed back to the machine and the actual mechanics of it to produce your parts. So all of those things need to be taken into account. So it's more like an ecosystem of feedbacks, if you will. But there's still a lot to do there, especially if the trend of the technology, I think, will be to continually to add more computational resource in those ways towards the machine, rather than having to download this information, bring it to a compute resource externally, bring it back in, much like you see the PCs and things moving towards system on a chip design, ARM methods and et cetera. I think that sort of trend will happen there as well. So that's one, I think, big gap, but it's a whole network of gaps. And then there is also trend towards parallelization within the manipulators and the systems themselves, and adding different energy sources and just controlling the systems as they get much more and more complex is also a challenge that I think is worth highlighting as an area that I think will need to grow in terms of the standards surrounding it.
Bill?
Thank you. Process control, it's a real issue. So I'll talk from an FAA standpoint. I think that there's a couple things to understand. That parts aren't certified, aircraft are certified. FAA only certifies 3 articles: an aircraft, an engine, and a propeller. And once you certify that, you get the type design. If it's a small aircraft, it's Part 23, large aircraft, Part 25. What's interesting is once you conform those drawings to your type certificate, you also have to certify the production process. And so that has to become a fixed process. And so that's what is so nuanced. So I think that's the first point. The second point is these are now called process intensive materials. There's no definition for PIMs. I would say process sensitive, to be honest. And the precedence is carbon fiber. So when we moved into carbon fiber, and really the icon is the 777 entry into service in 1994 by Boeing. Its empennage was all carbon fiber. And that was a huge move. I was at Raytheon at the time when they certified the Starship in 1985. It was a big move into Part 23 with the carbon fiber fuselage and wings. So that's the thing that we're talking about, is key process variables, and this whole idea of the unknown. You don't know what you don't know. So we have to control as much as we can, but we don't know because of the non-linearity, some of the coupling between some of the variables as we change. So Process control is a real issue, but what's interesting is how prescriptive, because once you really set that process control document in place, then the question becomes, how do you pivot off that based on equivalencies? And so we've spent a lot of time thinking about that as a committee through machine equivalency, material equivalency, and it's not a simple process. So process control is it wants to be as wide as possible to provide general guidance, but narrow enough such that you don't have significant variation to compromise the integrity of the final part.
Shane, did you want to jump in here?
Yeah, if I could just add, we all talk about a fixed process and understanding what your inputs are and controlling for all those throughout the whole process. As Amber said, not just the powder bed fusion process or your 3D printing, but until the end, until the part is finally inspected and put in a box and shipped. And but we have to be very careful as SDOs and people in the industry not to put ourselves in a box such that as new technology comes along, we are so down a path that we can't be flexible enough to take advantage of the new technology. When the feedback control, for example, of powder bed fusion becomes widely used, a lot of the things that we say now have to be fixed and controlled, you may not have to do that anymore. For example, the powder particle size distribution may not have to be so narrow, because if you hit a big clump of powder, for example, your feedback system would automatically adjust the heat so that you would still have a good deposition. And the way we think about spreading powder across the powder bed, that is evolving now as well. There are machines that don't use a touching recoater. So all of these things, as they evolve, we have to be careful that when we talk about a fixed process, that the people making the parts are allowed to determine what their inputs are and not prescribe just generally what those have to be, because as from the research side all the way to the standard side, everyone gets sort of involved in their world of, this is how I know additive manufacturing exists, this is the machine architecture I have, this is our process. But yet the rest of the world is quite larger in that regard. There are different platforms, the way different platforms work. There's multi-laser system, single laser system. There's material extrusion, the jetting process is different. So I would just say, caution us to be very careful about how we go into making these fixed process standards, that we don't put the part makers in a box so that the economics of the process don't make sense anymore, right? And the final example of that is, if we have to CT scan every part with today's technology, we'll never get there, because that's more expensive than making the part itself. That's just as an example.
Right, so we got about 15 minutes left. We've got questions coming in fast and furious here that I want to get to. I want to just turn the dial a little bit. There's one here that's been upvoted many times, and it has to do with testing. So the question is, how do destructive techniques, i.e. serial sectioning, help with the AM part qualifications and Q&C of the actual build process / machines when NDE is typically the focus? So if you want to address it in both the production and the R&D environments. Anybody cares to take a stab at that? Amber.
And this will be my last, because I have to run to another meeting, and I appreciate all the time and the questions here, and feel free for people, if you want to follow up, please do. But in terms of the serial sectioning and stuff, I think obviously we want to get to the NDE methods as
Seems like your audio has frozen.
Yeah, I think she had to leave sooner than she expected.
There you're back.
working.
No, go ahead. We can hear you now.
All right. So I was just going to say, yes, we want to move to NDT and the in situ. I think it just comes down to, you need to validate it, right? So at some point, yes, we want to trust those, non-destructive methods, but up front, and I think that's really where the R&D sector can really help out, is doing all that that validation work and that hands-on work so that we can get comfortable with trusting those NDT techniques. So, and again, thank you very much for the opportunity to speak, and hope
Thank you, Amber.
soon.
Okay. Anybody else want to have a go at that one on the use of destructive versus NDT? Yeah, Bill, and then Hallie.
I'll defer to Hallie. She's the probably closest to
You're such a
material
gentleman,
science.
Uh-oh. So basically, what Amber said is we have to really rely on R&D efforts first. There is a massive gap in standards for NDE for additive right now. It would be like going to the doctor to get an x-ray for your bones and the radiologist not knowing what a solid bone really looks like. So it's something as an industry that we really have to play catch up with. And I think standards organizations are starting to brew that effort, but you have to validate it all. So it's a massive R&D effort up front to generate the material and then validate it, and then eventually come up with standards for NDE. But right now, I think we're all sort of still stuck in the serial sectioning and hoping for the best method while we wait for NDE standards to be developed.
Okay. Bill, did you decide you had something you wanted to?
No, I did. I just wanted to defer to Holly because she's the material science. My opinion is cross-sectioning. This is a new paradigm. We're talking about highly anisotropic material. So it's before here's the danger of working with additive is we talked about a consolidated. You usually started with an ingot of casted ingot of titanium, Ti-64 or Inconel or aluminum. More or less, you could assume those properties are the same. And so once you process that material, then you look on the drawing. The drawing just calls out the material and then the heat treat condition. We don't have that luxury anymore. Because all of a sudden, as a design engineer, if you know what material it is, you know how it was post-processed, and all you need is the geometry. And assuming it's a commodity, it's a material that we've used, and most of the material, we've got 1.7 billion pounds of material used in aerospace. 70% of it is commodity materials. But we have design allowable curves where we know, based on the geometry, we can predict when it fails in ultimate load or in fatigue.
It's going to take quite some time before all of those standards are developed. But it's really important, I think, that when we are using the additive manufacturing in critical areas, the data package, what we've normally had, a TDIP, technical information data package, that ships with the part itself, now that's going to have to be a massive amount of information. And then the question becomes, how do you store that for 7 years of your QMS? So it's a big problem. It has many different heads and directions. We're trying to sort it out in the SDOs.
So we got about just 5 minutes left. I'm gonna throw out one more. Seems like it's a general question, and maybe you can tie it in with any closing thoughts that you want to make. So we'll go all the way around. The question is, aside from process control, what other important considerations are there in order to qualify an AM process? So if anybody wants to take a stab at that, or incorporate that in any closing thoughts that you might have. Bill, you got your hand up.
Let's be philosophical. What does qualification mean? So that's part of the problem. That the point that Shane made earlier, the whole issue of ontologies, we need to define our definitions first. So that's something we're struggling with. We're working on a document, AMS 7032, which is machine qualification. And there's installation qualification, there's operation qualification, there's the part level qualification, then you have the materials. And so that's part of the issue, is just defining what we're talking about. And even once we define that, then we'll have to understand the whole issue of how one thing is related to the other. When are you outside that lane? Once you, like I talked about before, you're highly prescriptive, you certify. Because there's really three things in the process. There's the machine, the software, and the material. And overlaid is the process control document that provides that prescription to get to an end part. But what's interesting is we don't fly flat panels with regards to carbon fiber composites. So even though we've generated these test coupons, the final structure, like a little bit before, the lattice, that dictates the structure, the microstructure of the part itself. So that's something that we have to understand. So anyway, it's the whole issue of qualification. I think we need to do a better job at working with the industry and sharing those lessons learned, especially because it's a very diversified field of machine builders. I think that's part of what's complicating sharing this information is that you've got 6 or 7 major OEMs and laser powder bed alone, and that doesn't necessarily help the sharing of information. So I think that is one of the many problems that we face.
So as an industry, what we're missing, and I'll say this across all the SDOs and all the industries, is that we do not have real good standards for part criticality. How you use the part and what's the terminology, what's the definition of the application that the part's being used in. And until we could say we can come to an agreement on what criticality means for space versus aviation, which may not be the same due to the operation and conditions and the requirements, then we can't predict what will ultimately be the best qualification process. Because if you're making a tertiary part that's holding up a bathroom wall, you may not have to qualify it the same way you would for a turbine blade. Those are completely different spectrums of use case, and the part criticality we need to come up with a good standard for that. And that's a work item that we have going on in ASTM now. And what I would hope that we could do is come up with a framework, whether you're in oil and gas, your criteria for criticality is going to be different, corrosion and all those things are different, but you have elements that will be the same. And if we can come up with a framework, then we would be able to, within each industry, have a better understanding of what's going to be required, how many cut-ups you're going to have to do, how many non-destructive testing, what the NDT will look like going forward. And that will drive what the real requirements are. Right now, we're kind of trying to prescribe, well, whatever process we might be using and say that's the way we're going to do it. Probably in the future, we'll have to think of it differently by part classification.
Thank you, Shane. Other thoughts?
It's Blake. I just want to, I'll take it like Bill from a philosophical or cultural high level. I think one thing to keep in mind, I guess, when it comes to specific AM standards is that standards have a sort of a lock-in effect, right? And the standards that exist today keep, to a certain degree, can keep a certain technology on a certain track. And I think there's some assumption that as AM will come in, it's another process, it will replace some other process and fit within that standard in certain contexts. I think in a lot of cases that won't necessarily be the case, and that standards will need to be customized to fit what additive manufacturing does or what it is, because it can be fundamentally different than other standards and the way we're going about producing parts. I mean, just simple examples, we cannot rely on isotropic property data for certain materials or things like that. That just doesn't make sense with the context of additive. So we certainly need to redevelop that. So they may look very, very different than the current existing standards. And I just think on an understanding of that and a realization that there's not a one-to-one replacement here in a lot of cases, and the standards will need to be sort of customized to the process, and that will probably take quite a lot of time and just understanding, I guess, and work from everyone involved.
Okay. Kate, Hallie, any closing thoughts? Hallie?
Sure. So for me, it's all about risk tolerance. The standards that we release, that we all volunteer to work on, at the end of the day, they really are just guidance documents. Whether the FAA and EASA or whatever federal governing agency is watching what you're doing and certifying you as flight ready or ready to go into a power plant, at the end of the day, it's up to each company and each industry to decide what their risk tolerance is. Like I've said before, additive is a 21st century technology. You know, we have the benefit of looking at it from a data-driven perspective, and I hope that we continue to do that. And I look forward to driving that from my end and working with the standards organizations to help basically bring that out into the rest of industry as well.
Okay. I guess, Kate, you get the last word if you want.
Last word. Okay. I just really echo what everyone else has said about process control. It really is going to be related to the end use and risk tolerance, as Hallie's just said. And, you know, definitely the more safety critical items will require more rigorous process controls. On another note, I just thank you for the opportunity to be here and the opportunity to learn from you all.
That's a good note to close on. Thank you all. Thank you, America Makes, and all of our speakers for being here today. Appreciate the audience interventions. And I guess with that, we're at time, so I will turn it back over to Brandon.
Thanks, Jim. Cheers all.
Thanks.
Thank you all so much. It's so great to see all of you. Thank you, Jim. Thank you all so much for your participation. I hope everyone enjoyed that discussion as much as I did. You know, I just wanted to make a quick note to the audience before we go on our break. You know, there's a number of projects that have actually occurred in this space at the Institute, and to just make folks aware, I mean, there's quite a number of them, and we have, you know, more than half a dozen ongoing right now in terms of AAPT, ATRQ. The Mammals program has been an excellent example of that, looking at part families like fuel-cooled oil coolers and bell cranks, for examples, to understand the underlying important considerations that go into attempting to qualify these types of products and better draw out our understanding of the surrounding necessary requirements for defining an additive manufacturing order of operations, right? Which is, I think, a great highlight of today's discussion. You know, one thing further, I just wanted to ask folks that are here, and, you know, if you've enjoyed the discussion today, and if there's a topic that you think maybe we could talk about next time, if you could put that in the chat while we're at the break, I would greatly appreciate that. We want to hear your thoughts. We want to hear about, you know, where you think we could be talking more about something and drawing out the narrative more definitively to help everyone. And so with that, I thank you all. We're going to go on and take a break now until 1:30. But yeah, I hope you enjoy. Come back, enjoy the conversation for the afternoon, and thank you all so much. Good afternoon, everyone. I hope you got a quick bite to eat or had a enjoying conversation during the break. So we're going to kind of continue the conversation around these ideas of control and qualification. In fact, the next discussion is an ongoing project at the Institute called ALSAM, Project 3024. And this is focused on leveraging, you know, prior investment across a number of programs, understanding advancements in machine control and hardware and software, and then leveraging that in a multi-heat source additive manufacturing powder bed fusion process. And so with that, I want to welcome Mike Tucker and Abdallah Nassar to the stage, and be great to see them. We'll give them just a second here.
Great. So Abdallah, you were invited to the stage, so you just have to turn on your camera and mic. Same with you, Michael Tucker. Feel free to turn on your camera and mic.
Hello, sir. Good afternoon. How have you been?
Oh, not too bad.
Great to see you.
Yeah, nice to see you as well.
Welcome, welcome. Are you going to lead us off, or will Michael?
I'm hoping Michael can join here for a second. So we'll give him another second here because I don't join till a little bit later.
So, you know what, while we're waiting, I mentioned a couple of projects just prior to the break. You know, we were trying to elaborate a bit on some of the work that's been conducted at the Institute in terms of process control and understanding qualification. I just wanted to list a couple of the project numbers for folks in case they were looking to maybe better understand what data is readily available. So some of the projects include 3006, which pertains to the belt crank program, 3007, which is looking at oil coolers, 3011, that project actually just wrapped up on feature-based qualification for directed energy deposition of TIE 64. We'll be hearing about a little bit later on today, one of the effective defects projects. The other one that was led by Penn State AFRL, that's actually wrapping up shortly, and that final report should be available soon. So those are projects 3012 and 3013. I mentioned AAPT, which is 3025, ATRQ, which is 3026. And then I'm going to go back and talk a little bit about some of the older ones as well, so people understand what's available there. So there was a lot of talk earlier this morning on NDE. There's actually been some really great work conducted that's out there available, looks at probability of detection and understanding complexities introduced by additively manufactured designs. So that's Project 4043, and there was a NIST-funded effort years ago, 1082. That project also explored visualization tool sets, as well as in-situ process monitoring technologies. There's also been some projects that have looked at other process monitoring technologies. So 4027 looked at a sensor suite that was developed by Sigma Labs, and it was tested against a couple of additive manufacturing powder bed fusion platforms. There was also the Reborn project that was led by Optimec years ago, Project 4037, that focused on understanding factors which contribute to product quality for laser powder-fed directed energy deposition. And then one of the more recent ones is Project 4045, and that was led by Raytheon Technologies, focused on development of a process for making heat exchangers. So if you need some help getting to those, give me a holler. Most of you have my email address, so happy to get you in touch and get you connected to these people. I think what we're going to do for the sake of time, Abdallah, if you don't mind, you care to take us on a journey?
Sure, no, I can start.
Thank you, sir. Welcome. Thank you for being here.
Absolutely. So let me try to get my PowerPoint up here. It'll just take me 1 second. All right, we'll have to just share my screen. Okay. All right. I hope you're able to see my screen now. If you're not able to, please. Okay, so I'm not going to do as nearly good of a job as Mike Tucker will do, but I'll try to present on his behalf until he's able to join. So this is Project 3024 on acceleration of large-scale additive manufacturing. It's being led by GE Global Research Center. Again, the PI is Mike Tucker, who took over from Bill Carter after Bill Carter retired from GE. And I'm Abdallah Nassar. I'm with the Applied Research Laboratory at Penn State University. I'm helping with some sensing and control work, as you'll see a little bit later. So the total funding for this program was on the order of $2 million, with a little under $1 million in cost share. Much of that was in kind contribution, and about 75,000 was cash. So puts us at a total budget on the order of $3 million, with a period of performance which comes to an end in mid-2022. The MRL level, we're going from a level 6 to a level 7, so very sort of applied work. Most of the work is going to be done on a machine that works, obviously, and will hopefully be able to operate in a production type setting. And this aligns with the processes swim lanes, and one example application is in process temperature gradient control.
Hi, can you hear me now?
I can, Mike. Would you like to take over?
Very sorry for that. My internet decided to crap out at the worst possible time. So yeah, thankfully I'm connected now, so thank you. Yeah, so our project team consists of 3 main project members. So I lead the team at GE Research. We have a team of engineers who are working on the open source controls for our Open M2 system. We also got support from GE Additive and, of course, Abdullah Nassar and his team, who you just met. This project is supported through the Air Force Research Lab, so we are grateful for their support as well as all the technical guidance through this project. And we're also getting some great technical input from Lawrence Livermore National Lab, who is providing, they're working on a parallel project on a similar multi-beam control system. At the same time, we have some interested participants, please go back, interested participants working on this project from Applied Optimization, and we're also getting some support from interest from Naval Research Lab as well. So these people are all stakeholders in this project. Next slide, please. So this project is the latest in a series of 3 projects. So starting before there was a GE Additive and back when America Makes was still fairly new, we began with Project 4039, which was to develop open source software and controls for end-to-end laser powder bed fusion AM systems. So input would be an STL file, the output would be fabricated part on a generic PBFAM system. The follow-on project to that at GE was the Project 4051, and this one took the open controls software and extended it to include hardware as well. So this added extensibility to the machine, so you can plug and play with different actuators and different sensors to extend the capability of your machines. So in parallel, Abdullah and his team on Project 4040 developed an open data acquisition system for monitoring, in situ monitoring of powder bed fusion processes. And this combined high-speed data logging of up to 100 kilohertz and low-speed data logging of machine status, and put together into a singular package. And these 3 led to our current project. Next slide, please. So the current project is on the acceleration of large-scale additive manufacturing. So you could think of acceleration in a couple of senses here. So on one hand, we want to accelerate the process itself, and that can be achieved through the use of multiple lasers working in parallel. But also you could think of it as accelerating the industry as a whole. So we are of the opinion that a high tide is going to raise all ships, and by providing this open source control system, this will enable the industry as a whole and the research community as a whole to advance powder bed fusion additive manufacturing. So on this project, we're bringing together the 3 projects I mentioned before, and we are deploying them onto a multi-laser concept laser M2 machine. And at the end of the project, this will be delivered to the Air Force Research Lab. Next slide, please. Okay, project schedule. So this project began about 2 years ago, and it's going to continue for another 1.5 years. So task 1 was the acquisition and installation of the machine, which was completed in June of this year. Next slide, please. And for this, we are taking an off-the-shelf concept laser M2-200 system. So this is the M2 with the improved gas flow system. It's 2 400-watt lasers, heated powder bed. And we took that system and we've applied our open control system to it. So this machine has been installed and calibrated and is currently sited at our plant in Niskayuna. Next slide. Okay, so jumping ahead a little bit to task 3. Task 3 is related to adapting the software and control system to support multiple lasers. And along with that, we have a series of experiments that we're running on behalf of the AFRL to vet the system and to help improve its capabilities, as well as to pick up and fix any bugs along the way as we go. Next slide. So in the first part, we had to take the scan path generation code from our previous project, which was written for a single laser, and adapt that to support multiple lasers. And as an example of what it is capable of, in the upper left, you can see one of the bracket entries from the GE bracket challenge on top of some supports. And using the scan path generator, you can generate scan paths similar to what you see below. So in the blown up image, you can see the plus sign shaped part, that is the supports. And then the other side, you see the part itself. And you can see that the scan paths shown by the vectors there, that they have different spacing, and also that you have contours around the part, but not, around the part, but not on the supports. So among the improvements that we made to the software, in addition to making it multi-laser capable, is now it has a spreadsheet-based configuration. Previously, it was a kludge of multiple different places where you input parameters. Now it's all organized. We implemented a single track experiment generator. So if you want to do parameter development studies, that's now facilitated by our new interface. We've added a capability to do variable layer heights by region. So for example, if you wanted to do contours at 50 microns and bulk at 100 microns, we now have the ability to do that within the configuration file. And we've also turned on some of the advanced scan techniques that are provided to us by the, in our case, we're using an RTC5 card to drive the scanners. So we've enabled skywriting, wobble, defocus, as well as a synchronized follow me mode, which I'll get into later. Next slide, please. The task 3.2 was to adapt the controller for the machine itself to support the M2-200. So it uses a slightly different communication protocol than we had in our previous project, which was on an M2 Classic. In addition, we've added, so the controller is LabVIEW based. You have access to the source code, and you can actually make changes to the code to add different devices, add different process blocks, and so on. So among the other updates we made, there's now a simulator that you can load and test build files before you go to run them on actual hardware. And on the back end, we've created a multi-laser wrapper for the RTC5 DLL. So this is what gives you access to all the functions of the RTC5, but it handles the distribution of the scan paths between the different scanners and the different modes of operation. Next slide, please. And as I keep mentioning, this whole software system is open, which means we intend it to be an open source project that is available to the America Makes community. It is hosted on a private GitHub site owned by America Makes. All you have to do is send me an access request, and you can, go crazy with the scan path generator and the multi-laser control software. So once you log in, you'll see there's three main repositories that you'll want to access. So one is precompiled binaries, that if you have a Windows 64-bit system, you can just immediately get up and running with a scan path generator. If you want to recompile the scan path code or to make changes to it, you can do that with the multi-laser scan path source. And finally, the multi-laser controller folder, that's the one that holds our LabVIEW controller as well as the RTC5 wrapper. Next. Okay, and the last part of task 3 was to conduct some experiments where we test out the multi-laser control functionality that we enabled on this system. So it starts with very simple experiments running up until very complicated experiments. And I'll walk through each of those now. Next. So the first experiment, so this machine was designated to run with Ti-64, so that's the material we're working with. And the study objective for the first experiment was to identify Ti-64 processing parameters that are suitable for building bulk structures and I guess I can qualify that even further, bulk structures with high processing rates. And as more of a basic scientific question, we wanted to identify relationships between the processing parameters and the meld pool morphology. So this was your basic single track experiment. To quantify things, we did cut-ups of the single tracks and some photography, which I can show you on the following slides. Okay, so to design the experiment, so again, we were looking at bulk parameters, so that's why you see fairly large spot sizes combined with high laser powers, and in this case, we can test out different stripes. So to design this experiment, we spaced out our parameter sets using normalized enthalpy as a parameter. And this is based on a wealth of literature and knowledge and input that we got from our friends at Lawrence Livermore. So they provide a lot of evidence that normalized enthalpy is a better predictor of melt pool morphology than, for example, volumetric energy density. So what we did is we created our experiment with logarithmically spaced parameter sets through normalized enthalpy space. Next, please. And so the results, these will be made available to America Makes members to review, but our tracks covered a broad range of normalized enthalpy as well as volumetric energy density, ranging all the way from barely melted through keyhole melting with porosity. And to objectively score each of these tracks, because ultimately you want to find tracks to continue building bulk structures out of, we came up with a scoring system to take measurements from the microscopy and to objectively pick out which are the best looking and the best behaved parameters. And what we found is that there is a strong dependency of the bead morphology on the normalized enthalpy, so a very strong relationship between normalized enthalpy and the normalized depth to width ratio. And we're going to work on publishing these results along with what's coming up in the next experiment. Next slide, please. So the second experiment took the results from DOE number 1 using the scoring scheme that I mentioned, and it down selected the top 5 parameter sets from the single tracks. And we also constrained it a bit more. We wanted 2 tracks out of the 50 micron parameter sets and 3 out of the 100 micron parameter sets. So that way we can get kind of a mixture of results. So in this experiment, we built up bulk cubes using different laser hatching or hatch spacing and different amounts of overlap between the 2 sides of the cube. So the way it was arranged is you'd have side A process first, then side B process second, with some amount of overlap in between. And the overlap ranged from 60 microns of overlap to 30 microns of separation between the sides. And as our outcome measurements, we did profilometry of the top surface. Well, actually, we're in the process of doing profilometry, which is going to be used to down select which samples we take the cross section of. So then once we take the cross sections, we'll look at them under the microscope and we can quantify porosity in the bulk of side A, the bulk of side B, as well as in the overlap region. Next slide, please. The third experiment was done in collaboration with friends at Applied Optimization, who are doing some super cool stuff with ScanPath software. And what's really neat is they are already working with the AllSam ScanPath software, and they're able to take the output of the scan paths that we generate, perform feature recognition on that output, apply a physics model or a thermal model, and based on that, they can modify the scan parameters for the individual vectors, as well as modifying the number of contours. And in this way, they can compensate for different challenging features in geometry. For example, down skins, different angles and different thicknesses of the part. And this is the output from their system. adheres to the XML schema that we derive through this process, and we're able to run this build on our machine. So these links that you see on the right side, they're actually inside of our machine right now, buried in powder. The machine just finished up late yesterday. We haven't dug them out yet. But in any case, yes, so we are able to run very complex scan paths with our software as well. Next slide, please. And to round out our experiments, we are testing out a new mode called Follow Me mode. And this involves the precise temporal and spatial synchronization of multiple beams. So the goal here is to control thermal gradients in both along the weld bead as well as tangential to it. And in this way, you might be able to influence the microstructure as well as the induced stress in the fabricated part. For the first experiments, we're just going to be doing characterizations on the synchronization itself. This is, again, learning to walk before you can run. So you can't really say anything about the gradients until you verified that your scanners are actually operating in sync. So for this, we'll be running some different challenge geometries through the through the machine software and evaluating the synchronization. Next slide, please.
Okay, so let me take over from here then. So a second part of this project is sensing of the process. The good thing about the LSAM software is that it gives you great capabilities to generate custom scan paths, to do things that you really can't do with commercial systems today. The bad side is, of course, it lets you do all this stuff, and so now it would be nice to be able to verify that the scanner actually did what you asked it to do, the timings are all correct, and that the resulting material properties maybe are along the lines of what you expected. So our task at Penn State AFRL was to design a sensor system based on some multispectral sensing technology that we've developed over the years, and to integrate that sensing hardware and software within the open M2 system that GE is designing. So our sensor, as I said, we call it a multispectral sensor, and the operating principle, if I can direct your attention all the way to the left, is that we are looking for process emissions, primarily emissions from the vapor plume that's generated during processing. So you have this big melt pool. Above the big melt pool, you have significant vaporization. That vapor may or may not interact with the incoming laser beam, but nevertheless, it's a very bright plume. So what we do is we look at the material system that we're processing. We determine which spectral bands are most appropriate for sensing that plume based on its anticipated emissions. So we look at databases from NIST and other places to see what emissions are lines one can expect with something like titanium. And then we insert our sensor, and based on previous data, we know that given a very low voltage, we know that we're likely not melting, not producing a lot of vaporization. At a given voltage level with not so much fluctuation, we know that we're in a reasonable processing regime. And then once you get to keyholing, you start seeing significant fluctuations in your signals, and that tells you that something is very unstable with your process. To do all this, what we need to do is we need a system that interfaces directly with the M2 system. So we have an FPGA-based system that also runs on a real-time computer that interfaces directly with the subcomponents of the machine. So our system directly interfaces with the control PC and the scanner cards, the RTC5 cards that are sending commands to the galvos. We also interface directly with the lasers on the machine. So we interface with both sets of scanners, both sets of lasers, as well as with our multispectral sensors. So everything is collected and synchronized both in time, as well as, very importantly, in position. We can store all that data and perform data analysis on it. The system operates at 50 kilohertz, which is the same speed with which the scanner communicates with the scanner control card communicates with the galvanometer. So we're hopefully not missing a whole lot during the acquisition process. Everything is saved to a database file that can be easily queried and identified later on. Another important aspect to this is that our multispectral sensors are installed in a coaxial configuration. Now, it's often not thought so much about, but there are some significant problems in trying to sense through the beam optics, especially because the beam optics are not designed for sensing. They're designed for transmitting a 1070 plus or minus whatever nanometer laser beam, right? So there are significant variations in reflectivity as you're scanning across your field of view. So to overcome that to some degree, we've devised a calibration system where we have a tungsten filament with a known voltage and current and temperature kind of profile, and we can move that tungsten bulb across the build plate. And at the same time, we have a protocol now established and tested where every time we move the light bulb to a new position, we also set the scanners to that position as well. So we're capturing what the intensity observed by our sensor is when the scanner is pointing at the light bulb. We take that data then to do a normalization or calibration of the data across the entire build plate, so we can now be confident that the trends that we are seeing aren't just a function of space, aren't just a function of where you are in the build plate. The additional advantage of using this sensor is that gas flow variations are known to be a very, very important factor in powder bed fusion AM in general. Leveraging the same technology that we've used for our calibration system, we've now are using that same system to do calibration or at least measurements of the gas flow across 90% of the build plate in situ, meaning that we can take our system, it's actually all self-contained in a container that goes into your build volume, and we can measure the flows across your build plate. We've demonstrated this system on our EOS M280, which we own at Penn State. We've also demonstrated that on the GE M2 system, but that wasn't ready in time for this presentation. For the EOS system, you can see, for instance, that if these measurements are correct, which we think they are, that there's quite a bit of fluctuation in the gas flow from the gas inlet side to the gas outlet side, where you're almost seeing a 2x drop in velocity across your build plate. Presumably, this has some effect on your processing. With the Concept M2 measurements that were just measured with their new gas flow system, we see almost very, very, very little fluctuation in the gas flow rate across the build plate. So it's quite impressive. And what this system allows us to do is establish a baseline for the system during operations so that we can compare one system to another system and make sure things are starting off on the right foot, if you will. And I'll turn it over back to you, Mike.
Okay, great. Thank you.
Sure.
Yes, so in terms of the timeline for the last couple of tasks here, so in the end, we are slated to deliver this machine to the Air Force Research Lab. Originally, we were planning to do it earlier this year, but due to some infrastructure projects over there, that's being delayed. So delivery will be towards the end of this year, after which we'll be providing on-site training and support to the AFRL personnel. So they'll be invited to come to our site, and hopefully they'll be up and running pretty shortly after it arrives there. Next slide, please. Okay, so here's our list of deliverables here. So yeah, the top two are related to the software. So again, those are available in their beta releases on the PBFAM GitHub site now. Penn State system is providing their sensor analytic and their sensor that's optimized for titanium. And yeah, it's also coming with a manual and yeah, the results from the experiments, which are also being made available to America Makes members. Next slide, please. All right, and so to give kind of an outlook and conclusion to this, so at the end of this program, this open software will have been deployed to at least 5 machines that we know of, 5 different types of machines even across the US, so including some that are GE machines, some that are homemade machines, some from other manufacturers. And it would just be so exciting if this was picked up by more researchers and more OEMs, that they'd be able to open up their machines and allow for real process development and real machine development research to continue. And so if you click one more time, so what I'm proposing is that as America Makes has supported this program for some time now, is that we work together and form an open source PBFAM users group. And so if you're at all interested in this, and I have heard from a number of people who would love to take their machines and open them up, please reach out to me and we'll see if we can drum up some support to make that happen. Okay, next slide. I think this is it. And yes, so I guess in this case, we finished up a little bit early and we are open to your questions.
Thanks, Mike. Thanks, Abdallah. That was an excellent presentation. We really appreciate the update. Looks like we got a couple of questions. So the first one asks about a written machine calibration procedure being part of the project deliverables. Is that going to be something to be anticipated by the membership at the end of the project?
So we've had some discussions with the GE business about this. So one of the things that we are providing is the equipment to do the OEM calibration. Now the procedure for the OEM calibration, that will be provided. And outside of that, because the system is open, people are also welcome to develop their own calibration procedures. Now, for example, with the new in situ sensing that Abdullah is adding, it might be possible to use the downbeam optics from one of the scanners to be able to calibrate against the other scanner. So this is one example of something you would be able to do in situ with the machine.
That's great. Did you have anything to add to that, Abdallah?
No, I just reiterate that. So all our sensing devices and the hardware and software are going to come with a manual, and we will provide a calibration procedure along with our sort of calibration stage system.
That's great. Yeah, you know, and to see the cross calibration potential there, that's exciting, and that it will allow for other sensors to be integrated and allow people to explore and learn. That's great. Next question here is curiosity about some of the logic and decision-making process of the program or project. It's asking why there was a decision to design your own FPGA instead of using a commercial off-the-shelf solution. Is there any insight you could provide there?
I don't understand the question, to be frank with you. We are obviously using an off-the-shelf FPGA
Okay.
that we are programming ourselves. That's what we're doing. We certainly don't design FPGA hardware. The code is what's important, and we have to, of course, write our own code to make the FPGA do what we want it to do.
Okay, thanks. There's another question we have here. We got a few more. It says there looks to be a lot of data to be collected. Are you anticipating down selection or downsize of the data that would be stored or reported for qualification and certification purposes? Are there going to be those types of features, I guess, available, or are you thinking about that?
So in terms of in-process data, sensor data, there is a lot of data. There are gigabytes of data, per layer. Maybe not quite so much, but there's a lot of data. For this approach, since this is meant to be sort of a research type system, an open type system, we are not downsampling that data. Now, currently, we are using a database format, an SQLite format. So when you load the data, you don't have to load the entire data set, right? You can load a subset of the data that you want to investigate. And if you want to do your own analytics on it, which we certainly do our own analytics, you can, downsample things as you go. In the future, if you have a metric that you really think correlates to your processing parameters, whether you've arrived at it using machine learning or statistics or anything else, you can certainly implement features so that you're not saving the entire data set. You're kind of downsampling your data and just saving that metric. But for this program, I do not believe we're going to save all the data. And you're either going to have to decide whether or not to filter that out post-process, which you can easily do. I mean, you can eliminate, for example, laser off points. That'll cut your data storage requirements in something close to a quarter or half. But we're going to save everything for now.
Okay. The next question asks, how do you think this work offers benefit for accelerating product or process qualification?
Well, so we've opened it up to everyone. So once you have this software, so you can go all the way back to the scan path generation software. You have control vector by vector of power, speed, focus, wobble, and so on. So you have like as low level control as you can get with the software. We're even providing the raw schema that gets fed into the machine controller so that you can write your own scripts, your own software to be able to enable new processes. And this is really far above and beyond what's enabled on OEM systems. And those open systems, they give you access to a very small subset of what the scanners and what the optics and the lasers are capable of. So by giving you access to really everything that you can do on the RTC5 card or on a generic scanner card, I think that we can explore a whole world of possibilities that hasn't really been explored yet. So to go back to the example with applied optimization, something they're doing is varying power levels along a vector. Now, in order to do that, you have to break up the vector into multiple vectors, but you're able to vary the power along a single line, which is a capability that isn't enabled on pretty much any OEM system that we know of.
So, and when you talk about that greater level of access, I'm thinking back over the years. I can remember one of the prior projects that led to this that Abdallah was on. So you're not only able to provide prescriptive information to the controller at a finer level of detail, but not only that, you have the ability to monitor the controllers themselves to understand their in-operation performance, right? Because you can actually extract out where the laser is, or at any point in time, given you're able to get in and monitor the controller behavior, correct?
Yeah. But you're logging the positions of the galvanometers along with the returns, the spectral returns. So yes, it's a level of feedback being provided by the in situ sensors that you don't necessarily get with other systems. And again, because it's all open, you can see the software, and if you want to see something different from its behavior or change what you're collecting and what you're looking at, you can do that.
Yeah, thank you. No, it's been, I know that conversation happened now a few years ago, and probably some people here today who might not have been there I think the closeout was at UTEP a couple years ago. I remember Abdallah and Jared giving a really great presentation on that project a couple years ago. So yeah, let me get in a couple more of these questions here. It says, have you been performing data analytics in real time during the build process?
Not on this program. On this program, we do all our data analytics post-process.
Okay.
And there's I don't want to get too far into the detail, but I mean, when we're in this sort of research mode, the question always is, say you want to correlate the data that you're getting to build quality. Well, how do you measure build quality? You measure build quality using post-process CT or post-process metallography. So that first step of saying, this metric correlates well to this output variable or this ground truth, you kind of have to do that post-process. So we're still not there yet where in situ we can say, aha, this metric is going sideways, so we should abort the process, or we should apply this feedback control.
Okay. The next one asks, are side A and B defined in the software as separate parts? Is overlap a function of how the models are placed in reference to one another? And does the control software define an STL surface offset?
Yeah, so in this case, one of the neat things about the open software is the way that you can hack it to design different experiments, like the one with the cubes. And so the way that this was implemented was by using separate STL files for side A and side B. And for that, you're able to specify what the offset is between the two halves of the cubes. Was the second part of the question? Sorry.
So you answered the first two parts. The last part asked, does the control software, or I guess the software, define a surface offset from the STL, the periphery of the STL, is what I'm envisioning.
Yep. Yes, so we took it as, so you can define offsets from the STL. So in this case, we're only doing hatches, but you can specify how far the end of the hatch is from the border of the STL file. But in this case, we decided to run the hatches all the way up to the border of the STL and move the STL itself to create the different separation. So there was some discussion before the experiment what the overlap should be defined as, so whether the vectors themselves overlap or if it's the weld pools that overlap, because that's a very important difference. And in this case, we decided to treat it as the vectors that are overlapped, because that's what's typically defined in ScanPath software when you're specifying, say, hatch spacing or overlap. You're looking at the vectors and not necessarily the melt pool.
Okay. Thank you. No, that's important to understand. We had a project with Ohio State here in the last 2 years, and there was a lot of discussion in that final report around those concepts as well. So I'm glad you clarified that. We're going to do just one more quick one, because it got upvoted so much. It says, what lessons are you learning from this effort which would be useful for improving AM cybersecurity?
So this is a topic that we can talk about, and if you want to talk about it at different levels, you can contact me directly. But our data acquisition hardware and software are independent of the machine hardware and software. That means that we can track what commands are sent back and forth on a vector by vector basis. Which essentially means that you have a record as close to ground truth as you're going to get of what was actually done on that system during operations. There are significant consequences to that in terms of identifying and potentially deterring certain vectors of I'll say attack. That's all I want to say about that.
That's fine. Mike, did you have anything to add to that, or?
Yeah, and I go back to, I remember, Abdullah, you once described it as like a fingerprint that you're collecting of a part. So when you look at the data that you're collecting, you should be able to control a print made one day to a print made another day. And by looking at the data, you should be able to say whether, based on the emissions that come out from it, whether you are printing the same part from one day to the next. And this gives you kind of a low-level assurance of cybersecurity that what you print is what you think you're printing. So it's even more important than thinking about the controller itself, because maybe that's not as important as the parts. People don't care so much about the printers as they do about the parts that come out of the printers, which is probably the most important part.
Great. Well, thank you both so much for being here today and giving us this update. I know I've really enjoyed it, and I really appreciate you taking the time out of your busy schedules. And Michael, thank you for joining us so late. I realize it's a little bit later there in the evening, so thank you, sir.
Oh, you're welcome. Thank you.
At this point, I'd like to welcome Chris Holzhauser from the Wichita State University National Institute of Aviation Research to the stage. He's going to give us a overview of the NCAMS process, a very important tool in materials and process qualification. It's great to see you, Chris. How have you been, sir?
Hey, Brandon, doing great. Thanks for having me here.
Oh, you're welcome. Thank you for coming and taking the time. I know you're super duper busy, but we really do appreciate it. So the stage is yours, sir. Thanks.
Absolutely. Thank you, Brandon. All right. Good afternoon, everyone. I'm hoping everyone can see my slides. I was told that in presentation mode that this gets a little cut off, so I'm going to try and navigate for you in almost full window mode. So as Brandon said, I'm Chris Holzhauser. I'm a research scientist for Wichita State University, specifically the National Institute for Aviation Research. And I'm here to talk to you more about another center that exists within the Institute called the National Center for Advanced Materials Performance, or NCAMP. And I know today's theme with the panel and all of the different SDOs you've all been exposed to, you know, we're really focusing on how does that relate to material and process control. And I'm also going to walk you through a little bit, not just NCAMP specifically, but how NCAMP fits in with all the other SDOs, and really ground us on the importance of process control and what that's done for us. So I actually have a little case study to kind of walk you through what's been done specifically for additive, and hopefully that'll give you some good frame of reference as we move into the next generation or the next round of emerging materials, and how that relates to process integration. So specifically, I think this goes without saying, just in general, the importance of material and process control. These are some specific guidelines that are out there through the lens, at least, of the FAA and others who really pay close attention to that. And these bullets here are probably of no surprise to anyone who are MMP-ers in nature. But it is worth pointing out, you know, composites into additive manufacturing materials, I think we can all agree that these are process-sensitive materials. And what that means is you really can't decouple the two from each other. And therefore, while process control has always been in existence, always been something that we talk about from a quality perspective, it does have a little bit of an extra nuance and extra level of difficulty that I'll get into when it's related specifically to AM materials. So I want this to be kind of ground level for us. This is what I'll keep coming back to, and I'll kind of show how NCAMP approaches this, and then how does NCAMP fit in with all the other SDOs, because I think that whole network is very important as we think about applying the MNP control lens, and then how does that work as we start to move from development into qualification. So I will reference this as kind of our case study. For those of you who are not part of the America Makes family at the time, there was a program out there that was America Makes funded as well as FAA funded, that we came together and we tested a lot of these theories and procedures that were in existence for other materials and other process intensive systems, specifically to Ultim 9085. So hopefully a lot of you have heard of this. There's some key things here, and really the takeaway that I want to point out is twofold. The first is the importance of process control, kind of witnessed by the graphs that I show here in the bottom right. That just shows what happens when you really understand all of the sub-elements that go into your system, and how that affects your material performance, and kind of what the expected outcome or what potential outcome could be when we look at kind of maybe what's right out of the box to what happens when we have a defined fixed process and all of these controls in place. And then most importantly, the documentation really that sits behind those process controls. And that documentation is then governed and transferred into a bunch of different SDOs to make sure that that's transferable, repeatable, that has the ability to expand into other areas. So when I talk case study kind of further down, I'll be referencing this because we are now a couple years after this program has concluded, and you can start to see the effects, the impacts, the results that we were able to do. And it's a nice story to see, okay, what happens after one of these projects are completed, just the path that we have to follow. Specifically, for those of you who are not familiar with NCAMP, I like this slide because it shows how we relate or how we sit positionally with other SDOs out there. So what comes to mind immediately, if you're going to zero in on the center of this, there are a few things that NCAMP does, which I'll go into that in just a bit, but it's really the connection to the handbooks that are out there, the guides that are out there, specifically MMPDS and CMH 17. I'll spend some time talking about CMH 17. So everything that we go through and create in NCAMP has a connection to those guides. We also have a connection to what we're calling here the approved specs, which in this case is specific to SAE. So I know you heard from Bill earlier today talking about the activities coming out of SAE. There is a natural connection that goes from NCAMP, CMH17, SAE, or MMPDS to SAE. On the flip side, we always have a lot of lessons learned that come from these qualifications. And those lessons learned serve as the opportunity to close gaps on testing standards. And so there's kind of a feedback loop that you see coming in the top of this graphic that shows our connection coming out of NCAMP to ASTM. And we're obviously very heavily reliant on data requirements, our test matrix, but more importantly, those test methods and those standards that allow us to go through a qualification. So this flow, it really is nice to just show how all of these things are interdependent and linked, which means that we are all, as best as possible, trying to coordinate and be on the same page and not divergent or redundant or conflicting. So real quick, so that's kind of NCAMP as it fits in the universe, let's call it. Let's go into just a little bit of background on NCAMP itself. So this was created in order to, as the slide says, accelerate insertion of advanced materials, of which, again, we can agree additive fits into that category. And really the outcome of this was to drive efficiency, while also hopefully creating less redundancy, which can drive down cost. It's not really about making a commodity, but it's making it to the point where we are normalized enough at the base such that we can all build upon a shared starting point. For those of you who are around or are familiar, maybe have heard the term agate. This is an evolution of the agate program, which was funded by NASA, industry, FAA, all coming together to say, hey, we keep seeing requests for essentially the same material. I'm trying to get X material onto my aircraft or onto my vehicle, and we're having to do an awful lot of redundant and repeated paperwork. Is there a better way of approaching this where we can create a shared database, and then again, everyone can leverage that? So that program lasted from 95 to 2002. I'm not going to go into the full history. It's a little blurry here. But you can see the evolution as we've progressed from that 2005 mark of agate, the creation of NCAMP, which is not just for small airplanes, as it says there, into acceptance by the FAA, acceptance of EASA, into where we are today, which is expanding beyond just composites, but into covering all advanced materials. And with that, what does that acceptance mean? So both FAA and EASA, shortly following, provided a memorandum that basically said, if you follow the NCAMP procedure and you are in compliant with that NCAMP process, such that at the end of the day, we have this shared database that is grounded by specifications, material and process specifications, we will accept that data. So as far as I'm aware, we are the only entity, the only institute that has this type of delegation authority. So this is a big deal, and we take this very seriously. So while we do have those memos with FAA and EASA, we do also do an awful lot of individual tailored work for the DoD around unique qualifications, and that's just not air vehicles, that can span to ground and sea as well. So what can you expect from the NCAMP process? I like this building block image. We actually use it quite a bit. It gives you a good feeling for, okay, what are we talking about as being shared? And this should be no surprise that we're usually talking at that coupon level, or maybe the very teetering into that first element level. That's what we consider shared. And we always talked about it when I was at Lockheed as maybe that 80% solution that doesn't necessarily get into specific application requirements, but it allows me to compare materials. It allows me to start to do some preliminary sizing and those types of things. And then it's once you start to get into application specific levels that starts to become proprietary. So that remaining 20% is a recognition that there's probably some additional testing, and there's good motivation for keeping those at the proprietary level. Some people ask me, what does NCAMP sell? What do they produce? So when you come to NCAMP and we're going through a qualification program, at the very basis, you're going to have to produce material and process specifications. And so when we think about process control and really material control as well, it's all grounded in the requirements that are defined in these specifications. So that's always our starting point. And in a lot of cases, those material and process specs are created from existing ones, either from the OEM or the supplier. They could also be from industry. And in a lot of cases, industry outpaces even the material provider here and wants to have key requirements defined. And so we will either take and build upon those, or we will, as a forming a steering committee and a consortium, will bring together experts and figure out what needs to go in the material and process specs. I will say, the first time through with Altem, we were sort of starting from scratch. We tried to show analogies to other process-intensive materials, but I think now where we've evolved over the last couple years, probably 4 years now, we're starting to create more of templates for this and setting expectations for what needs to go into material and process specifications. And then from that, we're able to create test matrices. Those test matrices are embodied in a test plan, and that test plan is what we use to generate the shared property data. It is worth noting, we do focus on the basic level of the building block, like I said before, and most of these, I'd say 90% of them are public. We do have the ability to keep some databases proprietary if the person funding it decides that that's the best way to go. So this graphic I always chuckle at because it was meant to simplify things, and it might not be the easiest to decipher, but this is a take of, okay, at the center we have our shared database and we have 2 different materials. And instead of all of the companies that you see here, A, B, C, D, all the way through J, having to reproduce that shared database, through the brilliance of what we call equivalency, there is a way for you to prove that your particular machine or your particular process can leverage the larger data set without having to reproduce this. And when I worked for Stratasys, I was often asked over my tenure there, how do I qualify or certify your materials? And I always scratched my head. I said, well, you do it like any other material. And that's still the case, but I really came to appreciate kind of where their confusion was. And it really aligned around all the different levels of qualification that we have to go through. And the sticking point was, do I always have to generate an allowable that's attached to a particular machine? So does my one serial machine, which may have a different personality than the one sitting next to it, do I need a data set for that particular machine? And I think this really solves the problem that I had back then in answering that question. Is it really comes down to that equivalency, and there's a lot of power in that equivalency and methodology. And so that allows us to, as we expand our knowledge, you can see through smaller testing programs, we can actually pool that data, and our database continues to grow if people are willing to share that data. A bit of an eyesore when we talk about all the steps that go into going through the NCAM process. We have a well-defined and approved SOP that we leverage, and this just basically shows you the process flow that we have to go through. And some of it has to do with creating representatives, engineering representatives that audit the process. There's inspection and representatives and AIR that's in there that's used to make sure that we can conform our parts both at the manufacturing level and then when we submit it for testing. So this is not meant for you to be able to absorb all of this. That's why these slides will be provided for you. But it gives you a good in-depth understanding of really what is taking place and what the expectations are for you as you approach a qualification. And really that top row there, we talk a lot about pre-qual work, which has to do with stabilizing the process, having the controls in place, and more importantly, having the process control document that really documents all of those elements to a T that is rev controlled and has traceability throughout this entire process flow. So this is a perfect lead up. Well, I did that excellently. So here are expectations when I really look at all of the documentation and what goes into that. Obviously, starting with the material spec, this references raw material, and then it references the feedstock that's going into the printer. In this particular instance, I call out a powder spec. For those of you who are doing kind of the powder activity, we know there's a reuse element here. which could be governed either at the material level or at the process level on how I handle powder reuse and recycling. We move down one level and we do have a process specification. This process specification really locks down and makes sure that we understand from a change control perspective where we are in time and what we have to accommodate as we progress through the evolution, the life cycle evolution of a particular material or machine. Within that process specification, we do reference a build PCD. Again, PCD is a process control document. Really throughout all of these steps, whether it's at the material level, the process level, the quality level, or the design value level, there's always PCDs that govern that. And I think that's something that people get confused by, because we throw the term around a lot. Sometimes it's misused and associated with the slash sheet. There are a lot of PCDs. They all need to be rev controlled, and they are all the, as I put it, kind of read a line, do a line type level of detail to make sure that my machine with its own personalities behaves like the fleet of other machines that it's supposed to behave like. From process specification, we really go into the NCAMP test plan. This allows you all to know exactly what we did and what went into creating our databases. And so there's a whole data pedigree out there that you really have to be sensitive to. And I'll give you an example of just what all we had to track through our initial program. And what we found is, and I'm sure a lot of people can appreciate this, you can't go back in a lot of ways in additive if I did not assign certain designations that followed my specimens throughout the entire process in order for us to do all of the proper analytics afterwards. So the data pedigree is very important. And then the test matrix is actually, what are we testing? Which there's still a lot of debate around what properties are needed at what conditions and what combinations of lots, machines, heats, etc. are we bringing together. And then lastly, what you can expect from us are two different reports. One is a material report, which basically is, here's the data. Do what you will with it. And then there's a statistical analysis report that actually leverages NCAMP specific statistics that are consistent with CMH 17. And so those are the reports that come out that everyone analyzes and uses, and what we will reference for our equivalencies. This is a very important, although simple, slide to note. When it comes to repeated material properties, all of these steps have to be in place. And what we found is, if at any time there's a change that happens all the way back to the raw material, all the way through the feedstock creation into the machine itself, we end up breaking this link. And so it's very important to stay relevant. We don't want to freeze people in time, but we can't lose visibility into, quote unquote, what's changed. And so there is the acronym there, ACN, which always gets spell checked to CAN on me. ACN is an advanced change notice, and we have mechanisms in place that we are evolving for additive that allows you to deal with things like obsolescence, software modifications, improvements on the quality side that actually solicits a change in your PCD, which means you have to rev that document, which means we have to rev our specifications. So this control linkage, I think, is very important for us to kind of keep in the forefront of our mind, just to make sure as a sanity check, hey, is what I'm about to do with this obsolete part going to break a linkage? And what do I need to do to verify and validate that I haven't invalidated one of my process controls that I put in place previously? All right, so we're going to get into a little bit of detail around that case study. So for those of you who are intimately involved with the Ultim program, some of this might sound like a repeat, but I will kind of share with you why this is important, because it's interesting to look now back on it a couple years. So here was our approach, and we really broke it down into keeping certain things constant and changing key variables at a time. I mean, this is sort of process control 101, right? If you change too many things and you get a different response, well, duh, how do I know what really did it? And we broke it down at the documentation level, at the system level, and then at the input level. So what can users actually manipulate? We also broke it into different areas based on physical and software. So a lot of those inputs could be CAD related. It could be dependencies really connected to even the test geometries that we were trying to evaluate. You know, is there an inherent variability in what I test because that test method was never really designed for additive? So we took it to this level where we evaluated everything that was out there, every configuration, almost, I'm exaggerating, a large amount of existing test methods were part of our study. And some of the outcomes of this really pushed us to, again, should not be a surprise, is understanding what forced us to form defects, and then being able to characterize the effects of those defects. And then from that, my documentation really zeroed in on identifying those sources and eliminating those sources up front, and then immortalizing that in our specifications. And this is probably a better way of looking at it when we start talking about subsystem level understanding. So I referenced before in the far right corner, coupon geometry. You can see those are tension coupons, D638s, a bunch of different types. Actually, the bar above the exaggerated dog bone was a modified 3039. So we did look at, again, a bunch of different ways of testing this. When it comes to data pedigree, you can see kind of the note around chamber location. I think the previous presenters that talked about their open source powder bed system, we know in powder bed systems that there is, at least without the controls that they talked about, some tendencies location-wise within the bed. So we know the larger you get, it's great, I can get more specimens out. But are there nuances even within the bed that I need to be able to characterize? We took it to kind of, I don't want to say an extreme level, but we felt it was important to really understand even what was happening as I put down material, so what we call toolpath planning. And even on the composite or non-metallic side, I should say, there is a microstructure that we were very worried about, and it was the disruption of that microstructure that we found to be our leading defect modes that had the greatest impact on our performance. And so by the end of this, we spent a lot of time actually using things like GoPros and some high-speed video to watch what's happening as the extrude comes out of my tip and is forming these types of defects, and then back figuring out all of the systems that came together to cause that defect. It's this bottom statement that really is daunting to a lot of people, and was probably the source of a lot of my questions on how do I qualify this material. We went through around 300 different inputs and parameters to understand which of those are the most sensitive, which ones can we actually measure, how can I improve upon them, and ultimately how do I lock them down. So I think what we've learned is we know how to get through that sensitivity screening a little bit faster. I think we know that you know, there's opportunity for us to maybe not exhaustively study all of those. But I will say that if you don't have an answer or data to back it up, someone out there in the audience will say, well, have you considered this? And we don't want to be at the beginning of a qualification saying, oh, I haven't looked at that. I don't know how that affects my performance. So we went through this exhaustive study, and I think there's a lot of good lessons learned that came from that. And this is a great example. So what actually did we end up locking down? There was a lot. There's a lot of files that go into what is fed to a printer. There is a lot of just information that we had to home grow systems, kind of to that Excel sheet that you see down below, just so I know exactly what the movement of my head is, that I limited and controlled what we call glueless move. So how far does the head move before it touches the next part? We made sure that our spacing was consistent, build to build. We made sure that we were capturing all of the different build locations. And so we had to document that somewhere. And one of the things that we ended up having to do is this kind of barcode thing at the bottom of the screen that you see there, just so that I know when I pick up the specimen, I can tell you exactly who made it, when it was made, what batch it was attached to, what material was used, where that material came from, the test condition that it was undergoing, where it was built, and what order it was built in. That's a lot of information on a barcode. And I bring that up because we had to piece all of this together, having gone through some maybe more painful, less successful programs in the past, and learning from our mistakes. and create this. And I bring it up because there are opportunity here to make a lot of this seamless, and that could be at the machine level, that could be even at NCAMP's level to institutionalize some of our learnings, which we are in the process of doing. But you can see here there was an awful lot that we locked down during the process, and then even after, kind of what I'm showing in the upper right-hand corner around fractography and fracture surfaces, we went back and took pictures, magnified pictures of all of the fracture surfaces that came from that qualification. So now we have that definition that can be used on other systems, on other machines, and other people who are trying to prove equivalency on what we did. You know, we basically created a repository of that information. So how does this work related to all the other SDOs that you heard from today? And I think this really speaks to the importance of getting things set up correctly so that those documents have a place to go and have a home to go in the future. So I'm just going to touch on several others, and you've probably heard from these entities early today in the panel. The first one that I just want to give a shout out to that I hope people realize, so CMH 17, Mill Handbook 17, although it says composites, is really an advanced material handbook, and they stood up a volume dedicated, I hope I got the terminology right, Cindy, a volume dedicated to additive manufacturing. So we've been meeting now for going on 2 years, and we are taking more people to participate in these working groups. So we have a data review working group, a material and process working group, of which I represent design analysis, testing, and statistics. So within CMH 17, what we're doing is we're going back and extracting all of those lessons learned and trying to put it in terms of, at least in my working group, you know, material and process specs. I'm sorry, not specs, guidelines. And it's not in order to reproduce what's already immortalized in the specification. It's really to put color around, okay, what is the applicability of this particular material? What are some considerations for materials in that category that need to be followed? And I know I'm running a little bit short on time, but you know, I bring this up because there is a lot of guidance out there, at least if you look in the PMC world or the Polymer Matrix Composite Volume 2H. You can see that we are driving guidance from this, and this really helped us inform kind of from the beginning what needs to go into our PCD and how that correlates to satisfying the requirements in our specs. I'm not going to go into great detail, but it does just give you a good idea of what the connectivity is between NCAMP and our data sets as it gets converted and reported in CMH 17. And this just gives you a little bit of process flow and expectation of how that works. We do have our own Yellow Pages procedure, which is like a balloting that you would find in any organization. And this is how we convert all of our learnings from NCAMP and get it out even further broadly disseminated through the CMH 17 lens. From that, I had mentioned other specifications. So some people are more geared and have their drawing system set up such they prefer to reference and procure to SAE specs. So there again is a natural connection for us to convert NCAMP specs into SAE specs. And so we've already got 2 of these out now. They're baseline specs related to Ultim 9085, talking about material extrusion, and the Fortis 900 MC. We are working on the next level detail, which are the slash sheets. Those have been balloted a few times. We still got some work to do there, but you can see from all of that initial work that we did on the America Makes / FAA project has now evolved into NCAMP specs and are now being published under SAE. And we are right now on the point where SAE is taking new sponsors for new specifications in the non-metallic space. We have a lot of work related to material extrusion and laser powder bed, not a lot on ceramics. So if anyone's got some nice lockdown and tightly controlled ceramic processes, we'd like to start to expand into that area. And then lastly, not to leave out ASTM, those lessons learned that I talked about before, a lot of it has to do with, does this test method apply to this particular material and process, have resulted in new work items. So the ASTM Center of Excellence is approaching it more from the testing side, and some of you actually participated in our round robin where we've come up with alternative D638 specimens. You know, kudos to Charles Park and Hector Sandoval on the Lockheed team to be offering up different ways of performing these tests. But really, because we were so successful with that program and the findings from that, it allows us to start filling in the gaps, first with just a guidance document on what tests work, what tests don't, and how do you sort of shoehorn them to work. And then more importantly, the ones down below are how do we expand and make dedicated ASTM standards, and I should say also ISO standards specifically for additive manufacturing. Last thing I want to touch on, a lot of this is made possible by the JAMS, Joint Center for Advanced Materials and Structure from the FAA. They are the ones that have questions that need to be answered when it comes to guidance, and they are the ones that are really pushing all of these different organizations forward collectively, such that we can rise all tides, so to speak, or maybe I butchered that statement. I bring this up because I wanted to just give you a feel for what's on the horizon. So we have a lot of activity that expands our research just so that we can take what we learned from ULTEM and grow it as a framework. I don't think anyone is in position to say, yep, we proved it, we did it, we're done. No, the point here is to show that it's applicable and transferable to other materials, to other systems. This is not a kind of a one-time thing. And so there's a lot that goes into that. And these are things that we've gone back and added to expand on our learnings. And what it's done for us is it's really positioned us to this, to start to take on different materials, more complex materials that start to bump our material performance. We're increasing the complexity of this, and we're actually moving away from non-metallics into metallics. So the next time I talk to this audience, you'll hear me talking about a new program that just got kicked off this month related to a titanium qualification. So I sort of just wanted to give you a little teaser there, but this shows you where we started, the power of the NCAMP process, and where we're trying to grow it. So with that, I believe that brings us to the end. I was only 5 minutes over.
You're fabulous. We started you a few minutes late, so no worries, Chris. We appreciate the update and some of the foreshadowing. Hey, one quick question, because I saw it come up a couple times here in the Q&A. Where can people find out more about this in terms of what's publicly available for them to get access to? Is there a website they can go to get some of this, or?
There absolutely is. So it's really easy. You can search NCAMP NIAR. It should pop up. I can get a link out to everyone. I'll actually add it. So Tara, when you send out the slides, I'll make sure that those links are available. There's a lot of public information already out there. Again, our specifications are available. Our standard operating procedure, NSP 100's out there. So there's opportunity there. And then of course there's good resources like myself, the director of the center, Royal Lovingfoss, and then Rachel Angelonis, who's the secretariat of CMH 17. All of these, there's such a wealth of knowledge there, and we love talking about this, and we'd be happy if there's something you're looking for, or you want to know more about how this applies to you, we'd be happy to sit down and talk with you about it.
Thank you, sir. Appreciate it. And so with that, I want to welcome Holly Martin to the stage. Holly's going to give us an update on a project. This is a mammals project. It's Project 3012. The team is looking at aluminum silicon 10 magnesium using laser powder bed fusion and understanding the effect of defects. So welcome, Holly. Hi, how are you?
I'm doing well, and yourself?
I'm doing great, thank you. The stage is yours.
Okay, thank you. So as Brandon mentioned, today we're talking about the effects of defects in laser powder bed fusion, aluminum silicon 10 mag. And so this is just a project overview of the funding we received and the cost share commitment, and where we're moving as far as the technology roadmap alignment. The main goal of this was to look at the metal additive manufacturing because it has the potential to provide replacement spare parts with reduced lead times, reduced inventories, and reduced costs. And to be able to do that, we have to look at the effects of rogue flaws on properties. And in the ability of the NDT methods, in this research, we looked at CT, RT, and PCRT to detect rogue flaws. So this project is lined up because there's not enough literature data to address these issues. So in order to do this, we started first with looking at the effect of the lack of fusion defects as well as powder contamination on both the mechanical properties and corrosion behavior of our alloy. We wanted to look at the deposition parameters to consistently generate our lack of fusion defects, then determine how various quantities of Inconel affected corrosion and mechanical properties as contaminants, and then look at the efficacy of in situ monitoring methods in NDT on detecting our lack of fusion defects. So the first thing we started looking at were the process parameters, our contamination levels, then build data for the mechanical testing, corrosion testing, NDT results, and lifing analysis is currently ongoing. So we had two main tasks in this project, the effects of lack of fusion defects and powder contamination. And so we're first going to start with the effect of lack of fusion defects. Sorry, my screen sort of flickered for a moment, so let me continue sharing. Sure, if I can figure out how. Okay, we're doing this again. Okay, sorry about that. So with our effect of lack of fusion defects, we first looked at requirement validation, then our part design, build planning, parameter development, study builds, and then characterization, and our service life analysis. With the characterization, we have NDT, our mechanical testing, and the corrosion testing in a neutral environment and an acid environment. So we specifically started with lack of fusion defects, which would give us the inadequate melt pool overlap. And so to do that, we used a ProX 320 on our aluminum powder. And then we started looking at different layer thicknesses, different powers, different hatch spacings, and different travel velocities. And we specifically focused on the ones you see underlined and bolded, as far as deviating from 60 microns to 90 and 120. We had a power of 370 and deviated from that with 350 and 320. We had a hatch spacing of 110 and then deviated from that with 130 and 150. And then velocity 1400 was our nominal parameter, and increased that to 15, 16, 17, and 1800 millimeters per second. And so changing those different variables, you can see in the left-hand corner as you're looking at your screen, this one right here, this is our nominal parameter set. And you can see that there are a few scattered defects in this particular image, but in general, very few. And as we decrease the power, our defects became more numerous and larger. Once we started from our nominal again and increased our hatch spacing, you can see we have larger defects as we move along with each of the hatch spacing, so they get larger and more numerous till we reach the 120. When we switch to the velocity, as our velocity change, once we change power, as our power decreases at a high velocity, you can see our defects get larger. And finally, when we compare large velocity with large hatch spacing, you can see that we get even larger defects. So I was just told my slides aren't changing, so let me pop back out. Okay, so we'll go this way. Can everyone see my slides still?
Yeah, we can see them. You're on the average length of defect.
Okay, great. Thank you. Okay, so when we look at this, the average length of the defects, one of the grad students involved on this project, he ran the statistical analysis on these guys and determined that as far as the Y44 build, our layer thickness had a more significant impact than hatch spacing, which had a more significant impact than power, which had a more significant impact than travel velocity. Power, I do want to point out, had a negative effect. So as power went down, you got larger velocities, larger defects. So it had negative because you decreased the power. We took that information and information from another statistical analysis and did a second build, which is the one you see at the bottom. That's build Y46. And power and hatch spacing they basically swapped places. And so power had a bigger effect than hatch spacing. So that's as far as the average length of the defect. When we look at the average height of the defect, same thing with Y44, the layer thickness, hatch spacing, power, travel velocity, that's the order of our significant, the significant, blanking here, significance. So there we go. When we switched to the Y46, there was no change in the impact between layer thickness, power, hatch spacing, and travel velocity, and that was for the average height of the defect. When we look at the defect density for just the Y44 build, the layer thickness, hatch spacing, power, and travel velocity matched up with the length and height of the defect. But once we went with the Y466, hatch spacing and layer thickness flipped, with power and travel velocity remaining. And so the ratio of defect length to height was affected: layer thickness, hatch spacing, power, travel velocity. With the Y466, power and hatch spacing actually did not have a significant effect. Only layer thickness and travel velocity did. So we used these statistics to come up to actually select our parameters for the goals we wanted to use for the rest of the project. We specifically wanted medium defects, which would be 150 to 200 microns, large defects, which would be 280 to 350 microns, and then small defects, which would be 100 to 140 microns. The reason we chose these sizes was with an aim towards detection in NDT, specifically CT. The medium defects we figured would be a gray area. The large defects we determined would definitely be detectable by CT, and the 100 to 140 microns, we were not sure that they'd be detectable by CT. And so we have a few images here showing our different goals, where we had the medium defects, the large defects, and the small defects. And so when we switch to our actual selection, We used, again, that statistical analysis that was performed on our screening builds to come up with the medium defects, which actually became small to medium defects. And we had a defect density that's close to 200. Our defect sizes were between 85 and 100 microns. And then, and we had to switch from the 150 to 200 because when we looked at our large defects, there actually were not any defects that were within our desired range. So we had to drop our large defects down in size in order to get large defects, which meant we dropped our medium defects down as well. So our average defect length for the large defects, instead of between 280 and 350, was between 115 and 196. And then finally, our last goal, because our medium defects got shifted to small defects, our third goal shifted from small defects to small defects with a high density. So goal 1 had a density of 200, whereas goal 3 had a density of 550. And you can see how each of these goals, as far as their parameters, differed from the nominal. To get our medium defects, we have a lower power. For the large defects and our mini small defects, we have the same power. The layer thickness we kept at 60 microns for the entire system. Hatch spacing stayed the same for goal 1. It went up some for goal 2, and it went up 70 microns for goal 3. And then our velocity also changed, increasing for all 3 from the 1400 of the nominal parameters. And so this is optical microscopy of the samples we took, the samples we built. You have build A, which is our nominal parameters on the left. So this one right here. You can see that we have relatively few defects with, an average, with a defect density of roughly 26 defects per centimeter squared. When we move to goal 2, which is our large defects, you can see that our defects are between 192.7 and 143.7 microns, with a density of 453 defects per centimeter squared. Our small defects and small number, which would match with goal 1, we have 174 defects per centimeter squared, and they are small. They're larger than the ones we have in our nominal parameters, which were 39 and 35. Our small defects are 90 and 87. When we come to goal 3, which is the mini defects, you can see that our defect sizes are roughly the same. We still have between 88 and 87, or 90 and 90. We just have a lot more defects with 565 per centimeter squared. So the first thing we did with this was take what would become our fatigue crack growth rectangular bars and send them out for CT analysis. And so these bars were arranged around a polymer cylinder. They were scanned at a 60 micron voxel size with data processed using an FG Studio Max. One thing I forgot to mention as I was talking about these is, in addition to goals A, 1, 2, and 3, which would match up with C, B, and D, we also looked at goals 2 and 3 without heat treatment to see what the effect of HIP had on the defect sizes. So what you're about to see is the X orientation of all of these prior to heat treatment. So if you would please play the X build orientation. Okay, so what you see is You first saw the labels, and now we're moving through the image as it plays, and you can see how the defects change throughout the image. B is our large defects. Then you have G next to itch, which would be small defects. D is the mini defects. E would be mini defects without heat treatment, and F is small without heat treatment. And you can see that F and G, excuse me, yeah, F and G, we built C, but then C ended up being built incorrectly, so we rebuilt it and we just labeled it G so we didn't get them confused. The two that are on top of each other, this would be G and this would be F. As that video played, you could see they were pretty similar. Then we had D and E that were pretty similar as well. We also have the Z orientation that was played. And so if you would please play the Z orientation. Like X, we first start off with the labels, and then we move through our system as we move through our samples as we go. So you can see again that our nominal parameters at the top left, followed by B, G, D, E, and F. G and F are basically very similar. D and E actually end up being very similar. And then B, with the Z orientation, seems to have fewer defects overall than when it was in the XY orientation. The defects you see, though, are larger in the B orientation than in the G orientation. So after the samples, those rectangular bars were scanned with CT, they were sent out for PCRT, which is process compensated resonance testing. Again, these were not heat treated. We did also send all of the samples that would be used later in the project, whether that was our high cycle fatigue samples or the tensile bars or the samples that would go for corrosion. All of that went to PCRT as far as the defects were. We did not do PCRT for the contaminated samples. So PCRT is a whole body NDT method. It evaluates a part based on the measured resonant frequencies using machine algorithms. You have your material, your sample that's placed in the system, and then a resonance scan is performed. The resonance that's the graphs that are produced are affected by the stiffness and the mass of the samples. So it's sensitive to your different material state or geometry. So it will show the difference in HIP and T6 after those are performed, as well as defects internal to our system. So after the part is placed on the fixture, then we have a transducer that drives the input across a range of frequencies. And so 2 more transducers receive the part's response, and they're evaluated against an acceptance criteria. And so this is an example of some of the data that was collected. You can see that both orientations of our build A, which were nominal, build B, which were our large defects, build G, which was our small defects, are very similar to each other. If you skip down to F, it shifted a little bit from A, B, and G, and then D and E are shifted a decent amount more. And so this is just showing that it is detecting differences between our samples. This technique is decently fast with 3 to 5 minutes per sample. It produced 20 plus resonance modes for each geometry. Again, like I mentioned, we did the rectangle bars, the E8 bars, and the E466 samples. And then they're able to take these resonances and identify outliers. So taking this information, they're able to plot the average frequency z-score and for each build. And so we have, you know, our 3 different orientations, X, Y, and Z. And so you can see that A and B and G, so we have nominal and A, B is our large defects, G is our small defects, are really similar across as far as the frequency score goes. Once we look at F, which would be our small defects, again, they're a little bit less than G. E and D, which are our small to medium defects and high density, you can see that E is much more closely packed than D is, and D has a very wide frequency. Part of that frequency comes because D has large defects scattered throughout our samples, and D is just, D is a not good sample. Now, these samples will, they will go HIP to T6. This was accidentally typed incorrectly. So A, B, G, and D all have HIP, then T6. E and F only have T6. And so even with our defects, we're able to see that right now our builds G and B fall in line with the nominal build. And so we're potentially seeing that HIP has some effect that allows those defects to be changed. The high cycle fatigue samples built to E466 standards were then run in 20 hertz with an R of 0.1. And what you can see is that our red samples, which are which are E, are not good. When we look at D, D is even worse than E. And so we can see that if we look at our nominal and then B, we can start seeing that the behavior of G is actually a little better than A. So the small defects had an effect, but it wasn't as negative as one might think. The larger defects, we did start seeing some decreases in the high cycle fatigue behavior, with them failing a little bit earlier. Once we start looking at the large defects, we see that they are just very poor. Our E samples, which would be the, they were supposed to be large defects, but if you look at the CT, I think we printed them accidentally as the mini defects. They actually behave a decent deal better than D. And then F performs a little bit worse than G, but F and E still perform better than D did. So overall, what you're seeing is that D has very poor performance compared to everything else. When we look at our tensile testing, you can see the yellow lines, which are D. A good number of our D samples didn't even make it into the upper bounds of our stress. They would typically fracture during loading or fracture before you even really reach the yield stress. Whereas our other samples, A was relatively better than everything else, but our samples of and then B was not great in comparison to A, but it was still far better than D. You can also see that our E's fell in line with D. And the other values, the other samples as far as our G's, they were relatively close to A as well. Again, so small defects alone are not creating an issue. With the fatigue crack growth rate, what we see is that our lower values of delta KTH were for A, B, G, and F, while the higher delta KTH were D, E, and F as well. Z had a lower delta KTH for F, while X had a higher one. And then DX actually had a lower delta KTH as compared to DZ. The highest KC toughness value was for AX and AZ, whereas our medium KC values went with GX, GZ, and low KC went with BX, BZ. We had very low KC values for DZ and EX. So once we moved to corrosion, what was interesting was with corrosion, at least externally, was you actually did not see a difference in behavior or a difference in appearance based on build or orientation. So you can see that as far as our machine samples go, they all look very similar. After 7 days, again, they all look very similar. 17 days, and then 28 days. And I'll be honest, we were sort of expecting that we would see a difference because as these were machined, you could actually see some defects on the surface of D and E. So we were expecting that those surface defects would lead to big pit formations, and it just did not in the appearance. Okay. We then looked at the behavior of the samples over the 28 days. First, we looked at the stress, and then we looked at the strain. And in general, if you're looking at the samples, our B and C samples behaved very similarly for the control in day 7. They did start splitting apart at day 17 and day 28. At day 17, the XY samples for both B and G were higher stress than the Z samples. And basically, the same thing happened for day 28. D, on the other hand, stayed very low in the stress until, strangely, we got to day 28. And what we really think is just that the samples were so difficult to work with that we got not necessarily better behaving samples on day 28, just maybe not as full of defects as earlier. They were the defects were highly varied throughout these samples, which is one reason we're thinking that. Okay, when we looked, so those samples were in, so all of this is in the neutral salt fog. I should have mentioned that. For strain, again, we see sort of the same behavior. Our samples for B and G are higher than for D. We see a split in orientations that we didn't see with stress. And then as the corrosion went on, our strain actually did decrease. If we look at stress, the stress really didn't change much for the 28 days, but strain definitely did decrease. And so that's likely due to just changes in the material as we have oxides that form and materials that just don't elongate as well as metals do. So as far as what we're doing with task 1, we have NDT of the HIP and T6, training for pass-fail to the mechanical data, and analysis of our builds A, E, and F in the neutral salt fog, and all of the analysis of A, E, F, B, G, and D in the acid salt fog. Next, with powder contamination, we have many of the same steps. We just don't have the lifing analysis that is also currently ongoing, and one of the next steps that just was forgotten there. The samples were produced on the Dayton Additive Research and Technologies SLM platform. They took the aluminum powder in 5 kilogram lots and then added a specific amount of the Inconel. The example we're showing is for 1%, but 1% was used as a screening build. And so CT was done on the powder, and you can see all of these bright spots within our samples, which are indicating the powder can a higher molecular weight material, which would be in this case our Inconel, and you can see when it was printed, the bright spots of the Inconel is there as well. Now this is 1%, again, a screening build. For the screening builds, we exposed it to a 0.25 molar hydrochloric acid solution to see what happened. 1%, we lost 56% of its weight in 7 days. 0.1% was a weight loss of roughly 100 milligrams per centimeter squared. It was something like 16%, no, excuse me, 8%. And then at the bottom, we have the uncontaminated. So we went with samples that were between 0.1% and 0%. And so we took a half of 1% and then a half of 0.05% to get our 3 contamination levels. So when we looked at those samples with tinsel testing, you can see that we have some samples that were much lower. These are the Z samples, whereas the samples that went higher were our X samples, or X orientation. This was regardless of contamination level. In addition, some of our highest contamination actually went a little higher as far as the ultimate tensile strength that they could achieve. And because it does contain nickel, we're thinking that the nickel does have an effect increasing the ultimate tensile strength. When we look at high cycle fatigue, we have our samples for the 0.1 and the Z orientation. We also have the 15 or 0% to the left. And if you look, the slight the 1.1% contamination actually increased the fatigue life from the ones that had a 0% contamination. So it is actually, in this case, the 0.1 is I'm not going to say a great thing, because ultimately corrosion will be affected, but it does seem to have some beneficial effect on fatigue life and on tensile testing. When we looked at intergranular corrosion with the contaminated samples, there was no demonstrable intergranular corrosion. For stress corrosion cracking that we were going to try to do, our U-bend bars they were printed flat, but when we tried to bend them after the heat treatment, they could not be bent to the appropriate section and to the appropriate shape. And if you do research on this alloy, it's not considered susceptible to stress corrosion cracking. For the samples, we have the immersion that's completed. Acidic salt fog has now been completed. The neutral salt fog is actually wrapping up tomorrow. So we will be examining these in tensile testing and then analyzing the data. So this is what I just mentioned. We have to finish these and analyze them. Then from there, Boeing, Lockheed, and Oerlikon will leverage this data for their qualification efforts. The monitoring and NDT data will benefit the full value chain, and the results will provide a greater confidence to the airworthiness authorities in understanding the potential behavior of rogue flaws. So we have had 3 master's students graduate from this project. UDRI has had undergraduates working on this project. So these deliverables will be coming available once this project is finished. So this includes the report and the raw data. And then, are there any questions?
Thanks, Holly. That was a great presentation. We really appreciate you giving that update. Yeah, there's a couple questions here. We could probably take a quick one or two. The first one asks, what's the advantage of using PCRT? Is it simply accept, reject, or does it actually identify defect location and size?
It is much more an accept, reject test. It does not give size at all. As far as location, it doesn't really give location at all, but it does say you can see based on how the resonance are going, the differences in defect behavior. And so I have this one image.
Mm-hmm.
Let me get back to it. Went right by it. The one figure from PCRT, there we go, where you can see the D samples, and each of these, we have the X or the Y or the Z, each of those has different defect densities, different defect sizes, and so based on how the behavior and the analysis went, you can see that it's like this sample down at the bottom is far away from what would be considered both acceptable and sort of
show you a little bit in this talk about some of our concerns there and what we're doing to address those with capabilities like AllSam. Next slide. It's a PDF, so it's kind of don't have, yeah, okay, there we go. So within AFRL, we've really been pushed to think about our transformational investments, and really been pushed to try and quantify, what capabilities are we trying to generate, what changes are we trying to make, and to that end, some of the goals that we have that guide our investments are items like trying to increase the speed. And what do we mean by that? 3x is kind of considered this success threshold. We're trying to reduce coefficients of variance, cost reductions on order 50% or even greater. And then really start to identify, what are the barriers that we can quantifiably reduce, and a lot of that's qual cert onboarding time. Excuse me. And to that end, we've got some ideas on general bins of investments in terms of the tech space that we'll make. And I think you see some of these being realized at the American Makes Institute. The multi/many laser qual cert is going to be a pacing issue for the Air Force. We've got a lot invested in selective laser melting technologies, and we'll likely do more. But the multi-laser aspects of selective laser melting are largely a untried proposition for end-use parts within an aerospace context. And so we have to start to understand, what's the value proposition of doing that? Is that the speed I mentioned above? Is it a cost reduction as well? What does it do to that, that coefficient of variance I mentioned? Can we exist in that trade space where we trade one for the other? Next slide. Really, we've made a lot of events at AFRL. We've made a lot of investments across the landscape of additive manufacturing processes. But as we get closer to production, we generally kind of focus on more manufacturing relevant or ready processes, things that are higher in TRL and MRL, and that kind of focuses our investments, I guess is the best way to put it. Right now, our engineering function, so kind of the organization AFRL notionally hands off identified prospects and candidates for maturation into production. The Rapid Sustainment Office, they're making large investments, again, in the area of productionizing selective laser melting and fused deposition modeling. Next slide. And this, just for your awareness, is some of the responsibility matrix, some of the interfaces between the different Air Force centers of additive investment. And AFRL is typically working in that higher risk space, and exploring and quantifying, doing an initial understanding of relevant processes and what they can potentially offer, identify things that need to improve or that we can make investments to make DoD requirements more achievable through process improvement, identify what the gaps for transitioning to the field are, and then really working with the industrial base to see what the pacing issues would be from an enterprise adoption level. Our rapid sustainment organizations somewhere in between there, in terms of they really start to work with the organic Air Force printing elements and manufacturing elements, and then also some, to a large extent with the industrial base, and then in the lower risk and higher TRL, MRL space, our sustainment centers are using additive technology on a daily basis, and they're really giving us a lot of the demand signals for what do we need to do better, particularly from a sustainment standpoint. Next slide. And in sustainment particularly, we have a process known as our change evaluation process. And so when we plan to substitute a casting for an additively manufactured part, we have to analyze 5 basic swim lanes of information that would give us a sense of how easy that transition is likely to occur from one manufacturing process to the next, and what we have to pay attention to. And these are fairly obvious in the first 3 categories, but categories 4 and 5 I think are really the pacing issues for additive at the moment, and that we don't have the validated analysis and methods established for additive part performance and life performance and process performance, perhaps. So validated process models. What does that look like for emerging capabilities? Is the process model for a selective laser melting process quite different when you add a second or a third or a fourth laser? I would imagine it would be, and those tools are pretty immature at this stage, but they are part of our airworthiness assessment, and when they're at very low levels of maturity, that's a cause for concern. Next slide. So how we've proceeded with additive in terms of qualification and certification in the early days of additive parts, we really looked at point qualifications, and this is an example of the F-15 pylon rib replacement. We were replacing an aluminum part with a titanium additive part, which gave us a lot of margin of safety. But we still had a very extensive campaign of part fabrication and monitoring and cut up and testing, on a per part basis, and it's very geometry dependent. It's not flexible. If we needed to modify the geometry of this part, a lot of that work would have to be redone, and it's fairly slow to do, relatively speaking. we're trying, we're now in the phase of looking at part family qualification. So for a frozen process like selective laser melting that we've optimized and locked all the parameters down on, can we, create a base level of design and quality that we can use to accelerate the certification of parts that meet that requirement. And so things like the F-22 bracket are flying, and soon to be followed by fuel oil coolers and propulsion adjacent devices like the oil pressure regulator or the aft sump cover. These are examples of part family qualifications where we feel like we create requirements for a particular part, which is important to actually engage the airworthiness process, but the part is representing a family of parts who have similar requirements, and it should accelerate the adoption of parts that are similar through certification by, or qualification by similarity. So next slide. But where we want to get to is process qualification to the point where we understand the limits of a process sufficiently well that we don't have to do part family specific exhaustive testing and quantification of performance. We have a much better sense of what a given manufacturing process can do. And to get to that level of insight, you need basically a continuous feedback loop of understanding of materials theory and the tools to employ that in practice and identify the parameter sets that are viable with a given process, and then couple that to the really challenging aspects of things like scan strategy and the geometry. This is because we have so much control over this process, we have a lot of details to manage at once, and frankly, that is going to be a challenge to getting getting to a qualification of a process as opposed to a part family using a process. I would estimate this is 10 years out or more, but we have started, and we are working to provide the level of knowledge of these processes so that we can, more rapidly adopt them for end-use parts. Next slide. And one of the key elements of developing that data for validating the process feedback loops of design, build, test, is creating those controlled experiments. And I think you've heard earlier about the ALSAM project, and that's the platform we feel we need to start to explore these capabilities and create those controlled experiments and understand things like overlap zones, like multi-beam collaborative material fabrication. In the bottom right, this follow me mode. What happens when you're able to modulate that beam at fairly high frequencies and do beam shaping, and perhaps what happens if you have 4, 8, 16 beams. These are all things that we have to have some insight into before we could even attempt to generate the models that we need to support design and analysis. Next slide. So we don't have ALSAM today. It is in aggressive development, I'll just say. It's nearing full operational capability. I think you got a sense of that earlier. But what we do have today to start exploration of some of these issues is our platforms that are commercially available. Like in this case, you're seeing a EOS M400 quad laser system. And so to see more immediate use of the commercially available systems, we pursued a program looking at creating a qualification methodology that would really look at perhaps not just single laser frozen parameter sets, but parameter windows or parameter spaces, I guess, in a multidimensional sense, that would be qualified to some level, and then really look at, I'd say, modernizing our methodology for getting the data to support the qualification assertions. And in that case, we're using AI and machine learning techniques to more rapidly or efficiently explore the parameter space and quantify sensitivities and interactions between parameters that we feel are critical to quality. Next slide. So, a major objective is that right now we don't have a single specification that the Air Force endorses, and then that's likely to be the case going forward. We participate in the review and development of many standards, but they have somewhat competing requirements. So we're in this project, we're trying to harmonize some of those requirements, find a minimum common set of experiments that would meet a large portion of each of these standards requirements. We think that's probably a useful exercise. It's not stake in the ground. We're not tied to meeting that particular set of requirements, but we're trying to understand what that would look like, and derive our approach from that. Again, I mentioned, we're trying to qualify a parameter set on a parameter space, not a parameter set. We think that'll be very useful. And honestly, that's the reality in many commercial settings. Maybe not for aerospace, but we think that to utilize laser systems in an efficient way, that'll be probably requisite. We're looking at two different materials. I mentioned the AI ML aspects. And then last but not least, we're going to try and, besides going to, making a qualification assertion, we're going to try and demonstrate it through some representative, functionally testable geometries at multiple production sites. So not just at our site, we're going to actually send this out to 2 service bureaus and see, can we reproduce to a large extent the performance. Next slide. So, just to give you some sense of what this program entails, again, it's kind of, you'll see top and bottom, the kind of 2 swim lanes for the materials, but they're largely following a similar process. And, we're now well on from the March timeline highlighted here and during the last program management review. But, I'd say we're still on track, and we're really getting, to the point where we have the parameter space developed, and we're going to start, working some of the validation and what we would say allowable development. So next slide. The Air Force has invested in exploring, what qualification looks like for single laser machines, and you can see it's kind of a fairly serial process. This step after that step after that step. We generate a lot of good learning there. We learn things when we perform this on multiple machines and aggregate data and compare notes between machines effectively. But it is very sequential. We're looking at, for a more modern statistical approach to evaluating the machine quality and that it meets the advertised claims, and that we reach a level that we can begin to design with. Next stage. Next slide. And to do that, we've enlisted the aid of Senvol, America Makes member, probably Annie or Zach are on the line. But, they've really helped us set up guide us through an initial DOE where we're looking at a combination of predictors and targets, looking at correlations between those. After, we do mechanical evaluations of specimens and physical evaluations, whether that's metallography, porosity evaluation, surface roughness, various mechanical tests. I'm starting to draw some, some essentially modeling of this high dimensional space between the predictors and the targets using machine learning algorithms. Next slide. from there, we set kind of stakes in the ground for our qualification. Here's what we need in this case for the aluminum. Can we define a parameter, with the aid of the models created through the machine learning? Can we create a window of parameters that would keep us in this range, these threshold values of material performance, which we think are adequate for that material? They created an excellent tool to help us explore kind of forward and backwards, what happens when we modify variables or ask for certain targets or certain coefficients of variance on some of those target properties. What should we explore for a parameter window? And then of course we are now, next slide, going off and evaluating those recommended parameter windows for actual, accuracy to the model, or the model accuracy to the mechanical specimens, I guess more properly stated. So right now, we've got kind of this proposed window for that we're going to validate, and so, we feel that, or at least the model's indicating that we should have a reasonable chance of achieving the mechanical properties thresholded on the prior page using this parameter set. And you can see there's some ability to vary the power there and say laser speed and a little bit on the hatch spacing. There's some sensitivity there, obviously. But I think that the interesting thing is that if you look on this chart where our initial parameter set was in the relevant 3 parameters, it was that blue star. So we're really, we started at one place, and I think this has really pushed us much faster and much farther than we probably would have gotten in any other way. So right now I'd say that at least from an exploration model, that's pretty successful. As long as our validation results come back even modestly correlative to the assertions of the model, then I think we'll be quite happy with kind of the process change this has enabled in terms of just changing the way we do our experiments. Next slide. And I think we're getting some of the initial results back, and they are kind of following within the desired parameter range. That's kind of that middle window there, where we have at least some data points with, in this case, just simple tensile static experiments. And we've also feel that we're going to move this into the dynamic regime as well, because at least our fracture mechanics based methodology says that that the say porosity targets that the machine learning models are predicting will make dramatic differences in the dynamic performance of this material. And so we have I'd say a fairly sensitive indicator of how powerful the models are or will be. Those fracture mechanics models have been validated pretty extensively using more conventional design of experiments approaches. So we have reasonably high confidence in that lower bounds that you're seeing there for the kind of maximum stress level based on a assumed initial flaw size, which is the pores in question typically. So we're going to move on to that stage in the very near future as a fairly sensitive check of how powerful the modeling approach is. Next slide. I think that might be the concluding slide. The next one. Yes. So I'll wrap up there. Brandon, are you going to moderate this, or do you just want me to work through the Q&A list here?
I can read them off for you, but I'm flexible here. I'll read you the first one, Mark. So it says, is there any work on developing alloys specifically adapted to additive manufacturing?
Is there any work? At AFRL, yes. It's a challenge there is that, those alloys are often pretty proprietary. And the parameter sets that are needed to print them well are super proprietary. So while we have small projects looking at those, I would characterize them typically as small projects just due to the challenges in terms of broad applicability. What we're doing here is we're taking two of the most conventional alloys for additive out there. And, I mean, you can flip back through the presentation. I gave you the parameters, right? I mean, that's not how, I mean, some academics work that way, but a lot, even there, do not do that. So we're really trying to work in a very pervasive space in terms of, how broadly we can apply some of the learning. I do think there is value in the additive specific alloys, and we, do make targeted investments there where there's a special need, but I'd say that the barrier to more sustained and substantial investment is you really have to show a transformational change in deliverables, and so it becomes a chicken and egg problem, right?
Yeah.
So go ahead.
Personal curiosity, and you might not be able to comment, but in the Advanced Manufacturing Olympics, there was a focus and one of the challenges on high strength aluminum alloys. Is that something that could be anticipated from the community that Air Force is going to continue to pursue?
We will certainly continue to pursue that. I think, high strength aluminums are an unsolved problem for the Air Force. We haven't found the right fit yet, and that's not all on the solution provider side. That's part of we're a big organization with a lot of different needs, and so finding the right high strength aluminum is in the eye of the beholder. And there's something 80-90 chief engineers for programs of record, and they each have their own answer to that. So I like, say, aluminum silicon 10 or F357 because it's kind of a material that we're not going to push too hard, and everyone's like, okay, yeah, I get it. I'm not going to use that in structural critical applications, but I can still use it for a lot of useful apps. And I think also, particularly in aluminum, a lot of our high strength demand signals come from parts that just can't be fabricated in a powder bed system because of size constraints. So even if I had the perfect material, I need something 10 feet long. How are you going to print that? It's not going to be powder bed. I think there are multiple challenges there, but that's not to say we're not interested and we're not investing there. And I think that the high strength aluminum space will continue to see investment as we see things mature. The Additive Advanced Manufacturing Olympics was very interesting. And the part I enjoyed the most with that portion you discussed is that the failure modes were so wildly different between the different materials. I really hadn't appreciated how significant a 2% versus a 6% elongation was until we did some compression testing on relevant components and saw really radically different failure modes. So it's not a continuum. I'll say there are discontinuities.
Let me just ask one more question. The second highest voted one, it says, what published information is available for reference to better understand considerations of interest for AFRL, DoD, in determining airworthiness?
So there are structures bulletins that our airworthiness authorities publish. They contain some of the initial thoughts and requirements, and there's a structures bulletin 19-01, which is again a public facing document. You can search it on the internet, find it. And I think airworthiness bulletin 13-014 or something of that nature that really talks more about process qualification concerns. It doesn't give a prescriptive method. It's here are the issues we're gonna here are some of the issues we're gonna ask you about. So again, it's kind of the Air Force is going to have their organic solution for manufacturing qualification, and that's going to be controlled information. But we also work with the standards development organizations, and it's kind of up to the provider to demonstrate quality, and that they have understanding of the limits on that quality, and then those limits will meet the requirements that the Air Force sets. And the Air Force will set requirements, at least for the foreseeable future, that are no different than wrought products or cast products. They're going to be performance typically based requirements. There's going to be damage and durability tolerance requirements. So they're not going to be, there are some additional additive requirements, and they're in those two documents I referenced, but by and large, it's the standard process.
Okay. All right, sir. Well, with that, I thank you so much for joining us here today. Really appreciated some of your insights and perspectives, particularly pertaining to the subject line of today, quality control and qualification. So, and it's good to see you.
Good to see you. Sorry I don't have my glamour light like I do at my home setup. I'm on the road at the moment, so.
No worries. No worries. Glad you could join us, though. And so with that, I'll welcome John Wilczynski to the stage. Help me out with some closing remarks. Hopefully, I'm not catching him too off guard.
No. I'm here. Nothing. No really exciting closing remarks from me other than thanks everyone for. I mean, this was, like I said when we started, quite an action-packed and full of content last 6 hours or so. So thanks for bearing with us, everyone. We've had really great participation throughout. A lot of people coming and going for different talks. I think, between the panel, getting it kicked off and uncovering, that really interesting back and forth or difference of perspectives from the standards bodies and what they're working with and how you engage with them. And, industry's perspective, which is ultimately what drives any of this work that needs to get done. I think that was a great way to start it off. A couple of really good closeout projects, continuing to build off the portfolio. So Brandon's mentioned it a couple of times. He's actually walked through a series of different projects that we've worked on. We encourage you, whether you're new or you've been around for a while, there's quite a bit of content out there available to everybody. And then as you look into that and have questions or interest in the work that's been done, there's quite a bit more access available to all members. And if you're a member and aren't aware of that, you need to make sure that you get your credentials set up for our digital storefront and are in position to take advantage of the information. So encourage everyone to do that. Reach out with questions. Again, this is all about getting engaged and working together. This Tucker said it earlier. This idea of the rising tide lifts all boats. I mean, we've said that for years. We've lived it for years. We believe in our role as the convener, coordinator, and catalyst of the additive manufacturing industry, and we can't do it without everyone that's on the phone and everyone that presented and consumed and is part of these projects and is part of road mapping. There will be many, many more opportunities. I don't see things changing a lot in the near term. We have expectations to continue to deliver virtual content. We'll be putting some more information out about that, specifically what it looks like, opportunities to engage with that. We have what's in front of you today, the save the date. We've laid out the next 2 years, basically for what we believe will be in-person events. Obviously, there's an asterisk next to that first one. But as of right now, these are the dates that we are locking in for the TRX events and MMX events for the next couple of years. And then we'll have quite a bit more content through webinars, through a new series that we're going to roll out on Fridays once a month, and a whole host of other opportunities to get engaged. A lot of hopefully exciting announcements soon about upcoming workshops on different topics. I think hopefully you saw the power of people coming together to generate something like the AMSC workshop, or excuse me, the AMSC roadmap. Ultimately, what that can result in and the impact that it had, the only way that works is if we're, working with the community to generate it. So look forward to working with many more on those topics moving forward. We have, I think, the floor set up, or the reception hall, if you will, for another half hour or so. So encourage everyone to go mingle, meet some new friends, and thank you, Dr. Ribick, for organizing all of this, along with Jim McCabe and Tara. Huge thanks to her for all the work that she does to pull these events together, get them promoted. We had over 500 people register for this, and hundreds participate over the course of the last day. So thank you to all. Appreciate your time.
Thanks, John.